Let us begin our journey to this remarkable moon, drifting outward from our familiar Earth, past the rusty deserts of Mars, through the asteroid belt with its countless tumbling rocks, beyond the mighty Jupiter with its swirling storms, until we arrive at the golden realm of Saturn. Here, suspended in the velvet darkness of space, encircled by those magnificent rings that have captivated human imagination for centuries, we find a family of moons unlike any other in our solar system. And among them, small but extraordinary, gleams the brightest object in all the solar system, reflecting nearly all the sunlight that touches its frozen surface. This is Enceladus, and tonight we will explore every chapter of its remarkable story. The tale of how humans came to know Enceladus begins on a clear August night in 1789 in the English town of Slough, where a musician turned astronomer named William Herschel was conducting his nightly observations of the heavens. Herschel had already achieved fame 8 years earlier with his discovery of Uranus, the first planet found since ancient times, and this accomplishment had earned him the patronage of King George III, allowing him to dedicate his life entirely to studying the cosmos. On this particular evening, Herschel was using his newest and most powerful telescope, a magnificent instrument with a mirror spanning 40 feet in length, the largest telescope ever constructed at that time. As Herschel trained his great telescope on Saturn, he was searching for new moons around the ringed planet. Saturn had been known to possess moons since 1655, when the Dutch astronomer Christian Huygens had discovered Titan, that large and hazy world that would later prove to have its own thick atmosphere and hydrocarbon lakes. Other astronomers had found additional moons in the following decades, but Herschel suspected there might be more, smaller companions hiding in the glare of Saturn's brilliant rings. His patience and his superior instrument would prove him right. On that August night, Herschel noticed a tiny point of light moving in concert with Saturn, clearly orbiting the planet rather than drifting as a background star would. Over the following nights, he confirmed his observation, tracking the small moon as it completed its orbit around Saturn. He had discovered what we now call Enceladus, along with another moon, Mimas, found on the same evening. It was a remarkable achievement, made possible by the combination of Herschel's dedication to building ever larger telescopes and his meticulous observational techniques. Herschel himself did not name his discovery. That honour fell to his son, John Herschel, who decades later suggested naming Saturn's moons after the Titans and giants of Greek mythology. Those powerful beings associated with the god Saturn, known to the Greeks as Cronus. The name Enceladus was chosen for this small bright moon, connecting it forever to that buried giant of ancient legend. John Herschel could not have known how fitting this name would prove to be, for just as the mythological Enceladus was said to be restless beneath Sicily, so too would this moon reveal itself to be geologically active, spewing material from its interior in a display that would astonish scientists more than 2 centuries after its discovery. In those early years following Herschel's discovery, astronomers could learn very little about Enceladus beyond its basic orbital characteristics. They determined that the moon completed one orbit around Saturn approximately every 33 hours, moving along a nearly circular path at a distance of about 238,000 kilometres from the planet's centre. They could estimate its size only roughly, suggesting it was perhaps a few hundred kilometres across, making it one of the smaller moons in Saturn's system. The moon's exceptional brightness was noted, with Enceladus reflecting more light than any other body in the solar system relative to its size, but the reason for this remarkable reflectivity remained a mystery. Throughout the 19th century and into the 20th, Enceladus remained a tiny, enigmatic point of light in even the most powerful telescopes. Astronomers refined their measurements of its orbit, discovering that it moved in a gravitational dance with another of Saturn's moons, Dione. For every orbit Dione completed around Saturn, Enceladus completed exactly 2, a relationship known as an orbital resonance. This gravitational connection would later prove crucial to understanding why Enceladus is so geologically active, but at the time it was simply an interesting mathematical curiosity. The space age brought new possibilities for studying the outer solar system. In the 1970s, NASA began planning what would become known as the Grand Tour, an ambitious series of missions to visit all the outer planets by taking advantage of a rare alignment that occurs only once every 175 years. This alignment would allow spacecraft to use the gravity of each planet to sling themselves onward to the next, visiting Jupiter, Saturn, Uranus, and Neptune in a single extended mission. From this planning emerged the Voyager program, 2 identical spacecraft that would revolutionize our understanding of the outer solar system and provide humanity's first close-up views of Enceladus. Voyager 1 launched on September 5, 1977, followed by its twin, Voyager 2, just 16 days earlier on August 20th. Despite launching second, Voyager 1 was placed on a faster trajectory that would bring it to Jupiter and Saturn ahead of its sibling. Both spacecraft carried identical suites of scientific instruments, including cameras capable of capturing images far more detailed than any Earth-based telescope could achieve. As the Voyagers raced outward through the solar system, scientists eagerly anticipated what they might reveal about Saturn's mysterious moons. Voyager 1 reached Saturn in November 1980, passing within 202,000 kilometers of Enceladus during its flyby of the Saturnian system. The images returned were revolutionary, showing for the first time that Enceladus was not simply a dead, cratered ball of ice like so many other small moons. Instead, the spacecraft revealed a world of surprising complexity, with some regions heavily cratered and ancient-looking, while others appeared smooth and young, suggesting that something had resurfaced them relatively recently in geological terms. The moon's diameter was measured at approximately 500 kilometers, making it small enough to fit comfortably within the borders of Arizona or the length of Great Britain. The smoothness of some regions on Enceladus puzzled scientists. On a small cold moon so far from the sun, there should be no source of energy to drive geological activity. Enceladus should have been frozen solid billions of years ago, its surface recording every impact it had experienced since the early days of the solar system. Yet here were vast plains almost entirely devoid of craters, surfaces that could only be explained if they had been renewed somehow, covered over by fresh material that had erased the scars of ancient impacts. What could possibly be generating enough heat within this tiny moon to allow such resurfacing? Voyager 2 arrived at Saturn in August 1981, passing even closer to Enceladus and returning additional images that deepened the mystery. The spacecraft confirmed the presence of both ancient cratered terrain and young smooth plains, and revealed intricate patterns of fractures and ridges crossing the moon's surface. These features suggested that Enceladus had experienced significant tectonic activity, with its icy crust being stretched, compressed, and broken by forces from within. But the source of these forces remained unclear. One observation from the Voyager missions would prove particularly significant, though its full importance was not recognized at the time. Scientists had known since 1966 that Saturn possessed a faint, diffuse ring far beyond the main ring system, a tenuous band of tiny ice particles known as the E-ring. The Voyager spacecraft confirmed that the E-ring was densest at the orbit of Enceladus, suggesting that this small moon might somehow be the source of the ring's material. But how could a frozen moon be supplying particles to a planetary ring? The answer would have to wait for a more capable spacecraft and a more thorough investigation. The Voyager encounters, brief as they were, transformed Enceladus from a point of light into a real world, a place with geography and history and mysteries demanding explanation. Scientists began developing theories to explain the moon's unexpected activity, most focusing on the gravitational interaction between Enceladus and its neighbouring moons. The orbital resonance with Dione, they suggested, might be flexing Enceladus's interior, generating heat through a process called tidal heating. This same mechanism was known to power the volcanic activity on Jupiter's moon Io, the most volcanically active body in the solar system. Perhaps something similar was occurring at Enceladus, though on a smaller and icier scale. But testing these theories would require a dedicated mission to Saturn, one that could spend years studying the planet and its moons rather than racing past in a matter of days. Such a mission was already being planned, a collaboration between NASA and the European Space Agency that would become one of the most successful planetary exploration missions in history. This mission would be named Cassini-Huygens, after the astronomers who had contributed so much to our early understanding of Saturn, and it would reveal Enceladus to be far more remarkable than even the most optimistic scientists had dared to imagine. The Cassini spacecraft was a marvel of engineering, the largest and most complex interplanetary probe ever built at the time of its launch. Weighing over 5,600 kilograms fully fueled, it carried 12 scientific instruments designed to study every aspect of the Saturnian system, from the planet's atmosphere and rings to its diverse family of moons. Attached to Cassini was the Huygens probe, built by the European Space Agency to descend through the thick atmosphere of Titan and land on its mysterious surface. Together, they represented decades of planning and construction, a testament to human curiosity and ingenuity. Cassini launched on October 15, 1997, beginning a 7-year journey to Saturn that would take it past Venus twice, back past Earth, and onward past Jupiter, using each planet's gravity to boost its speed and bend its trajectory toward the outer solar system. This complex path was necessary because no rocket then available was powerful enough to send such a massive spacecraft directly to Saturn. Instead, Cassini played a cosmic game of billiards, bouncing from planet to planet until it had gathered enough velocity to reach its destination. The spacecraft arrived at Saturn on July 1, 2004, firing its main engine for a nerve-wracking 96 minutes to slow itself enough to be captured by the planet's gravity. As Cassini settled into orbit around Saturn, it began a mission that would last 13 years, far exceeding its original 4-year plan. During this extended mission, Cassini would make over 100 close flybys of Saturn's moons, including 23 dedicated encounters with Enceladus that would transform our understanding of this small but extraordinary world. The first hints of what was to come arrived in early 2005, when Cassini's instruments detected something unexpected in the space around Enceladus. The spacecraft's magnetometer, designed to measure magnetic fields, noticed that Saturn's magnetic field was being disturbed near the moon, deflected as if something was pushing against it. This disturbance suggested that Enceladus was somehow affecting its surrounding environment, perhaps by releasing material that was interacting with the charged particles trapped in Saturn's magnetic field. But what could a small icy moon be releasing into space? The answer came on July 14, 2005, during Cassini's closest flyby of Enceladus to date. As the spacecraft passed just 175 kilometers above the moon's surface, its instruments detected something astonishing. A plume of water vapor and ice particles erupting from the Moon's south polar region. Enceladus was not a dead, frozen world at all. It was actively venting material into space, shooting geysers of water ice high above its surface in a continuous display of geological activity. The discovery electrified the scientific community and immediately elevated Enceladus from an interesting curiosity to one of the most important targets for exploration in the entire solar system. Subsequent flybys confirmed and expanded upon this initial discovery. The plumes were not emerging from random locations, but from a series of parallel fractures near the Moon's south pole, features that scientists quickly nicknamed the tiger stripes, due to their appearance in infrared images, where they showed up as warm lines against the cold background of the icy surface. These fractures, formerly named Alexandria sulcus, Cairo sulcus, Baghdad sulcus, and Damascus sulcus, after cities associated with the ancient tales of the Arabian Nights, were the sources of Enceladus's remarkable activity, windows into the Moon's interior through which material from below was escaping into space. The tiger stripes stretch across Enceladus's south polar region, each one roughly 130 kilometers long and spaced about 35 kilometers apart. They cut through the Moon's icy crust like great wounds, their edges raised slightly above the surrounding terrain. Their floors dropped below. Along their lengths, the ice is fractured and jumbled, evidence of the tremendous forces that created and continue to modify these features. And from dozens of individual vents distributed along the tiger stripes, jets of water vapour and ice particles spray continuously into space, feeding Saturn's E-ring and announcing to the cosmos that this small moon is very much alive. The warmth of the tiger stripes was one of their most surprising characteristics. Enceladus receives very little heat from the distant sun, and its small size means it should have lost any primordial heat from its formation billions of years ago. Yet Cassini's infrared instruments measured temperatures along the tiger stripes that were significantly warmer than the surrounding terrain, reaching as high as -85 degrees Celsius in some locations. While this might sound frigid by earthly standards, it was far warmer than the -200 degrees Celsius that would be expected on a passive icy surface at Saturn's distance from the Sun. Something was generating heat inside Enceladus, and that heat was escaping through the tiger stripes. The most likely explanation for this internal heat is tidal flexing, the same process that had been suggested after the Voyager encounters. As Enceladus orbits Saturn, it experiences varying gravitational forces due to its slightly elliptical orbit and its resonance with Dione. These forces squeeze and stretch the Moon, flexing its interior and generating heat through friction, much as repeatedly bending a paperclip causes it to warm. On Enceladus, this tidal heating appears to be concentrated at the South Pole, perhaps due to the particular way the Moon's interior responds to the gravitational forces, and this heat is what drives the plume activity and maintains the tiger stripes as active features. But tidal heating alone could not explain everything Cassini was discovering about Enceladus. The plumes were not simply water vapour escaping from warm ice. They contained a complex mixture of compounds that spoke to remarkable chemistry occurring within the Moon. As Cassini flew through the plumes on multiple occasions, its instruments analysed the composition of the ejected material, building up a detailed picture of what lay beneath Enceladus's frozen surface. And what they found suggested something extraordinary: a liquid water ocean hidden beneath the ice, an ocean that might possess the conditions necessary for life. The evidence for a subsurface ocean came from multiple sources, each adding another piece to the puzzle. The composition of the plumes included not just water vapour, but also salts, suggesting that the water had been in contact with rock and had dissolved minerals, just as Earth's oceans have done over billions of years. The presence of silica nanoparticles in the plume material indicated that hot water was interacting with rock at the bottom of the ocean, conditions reminiscent of hydrothermal vents on Earth's seafloor. And careful measurements of how Enceladus wobbles as it orbits Saturn, a motion called libration, revealed that the moon's icy shell was not frozen solid to its rocky core, but was floating freely, decoupled from the interior by a global layer of liquid water. This subsurface ocean is one of Enceladus's most remarkable features, and understanding its nature has been a major focus of scientific investigation. Based on Cassini's measurements, the ocean appears to be global, extending beneath the entire icy shell rather than being confined to the South Polar region. It lies perhaps 30 to 40 kilometers beneath the surface, trapped between the outer ice shell and the moon's rocky core. The ocean's depth is estimated at around 10 kilometers on average, though it may be deeper beneath the South Pole, where the ice shell appears to be thinner. In total, Enceladus's ocean may contain about as much liquid water as all of Earth's oceans combined, a staggering amount for such a small world. The composition of this hidden ocean has been revealed through analysis of the plume material. The water is salty, containing sodium chloride, the same compound that makes Earth's oceans taste of salt, along with sodium carbonate and sodium bicarbonate, compounds associated with alkaline conditions. The ocean's pH appears to be between 8 and 9, similar to soapy water, and indicating a mildly alkaline environment. This chemistry is consistent with water that has interacted extensively with rock, dissolving minerals and reaching a chemical equilibrium over millions or billions of years. Perhaps the most exciting discoveries about Enceladus's ocean chemistry came from Cassini's detection of molecular hydrogen in the plumes. Hydrogen gas is produced when water reacts with certain types of rock at high temperatures, a process called serpentinization that occurs at hydrothermal vents on Earth's ocean floor. The presence of hydrogen in Enceladus's plume strongly suggests that similar reactions are occurring at the bottom of the moon's ocean, where hot water is circulating through the rocky core. This process would not only produce hydrogen, but would also release energy that could potentially support life, just as hydrothermal vents on Earth support thriving ecosystems in the complete absence of sunlight. The detection of complex organic molecules in the plumes added another dimension to the case for habitability. Cassini's instruments found a variety of carbon-containing compounds, including large complex molecules with masses suggesting they might be hundreds of atoms in size. While these organics are not themselves evidence of life, they demonstrate that the chemical building blocks for life are present in Enceladus's ocean. Combined with the liquid water, the energy from hydrothermal activity, and the chemical nutrients dissolved in the ocean, Enceladus appears to possess all the basic requirements for life as we understand it. The ice shell that covers Enceladus's ocean is not a simple, uniform layer, but a complex structure that varies in thickness and properties across the moon. At the South Pole, where the tiger stripes are located, the shell is relatively thin, perhaps only a few kilometers thick, allowing heat from below to escape and material from the ocean to reach the surface. Elsewhere, the shell is thicker, reaching 20 to 25 kilometers in the moon's mid-latitudes and northern regions. This variation in thickness affects how the shell responds to tidal forces and may help explain why the plume activity is concentrated at the South Pole. The tiger stripes themselves are fascinating geological features that have been studied in detail through Cassini's many flybys. Each stripe is a fracture in the ice shell, a crack that extends down toward the ocean below. The fractures open and close as Enceladus orbits Saturn, responding to the changing tidal forces like slowly breathing wounds in the moon's surface. When the fractures are open, material from the ocean can escape through the vents, producing the plumes that Cassini observed. When they close, the flow diminishes. This tidal pumping helps explain the variations in plume activity that were observed over the course of Cassini's mission. The individual vents along the tiger stripes have been mapped and studied, revealing over 100 distinct sources of plume activity. These vents are not uniformly distributed, but are concentrated in certain areas, particularly near the ends of the tiger stripes, where the fractures are widest. The jets from these vents can reach heights of hundreds of kilometers above the surface, sending ice particles on trajectories that carry some of them entirely out of Enceladus's gravitational influence and into orbit around Saturn, where they become part of the E-ring. Other particles fall back to the surface, coating Enceladus in a continuous snow of fresh ice that helps explain the moon's extraordinary brightness. The relationship between Enceladus and Saturn's E-ring is one of the most beautiful examples of moon-ring interaction in the solar system. The E-ring is the widest of Saturn's rings, extending from the orbit of Mimas inward to beyond the orbit of Titan, a span of nearly 1 million kilometers. Yet this vast ring is incredibly tenuous, composed of tiny ice particles that are constantly being lost to various processes and must be continuously replenished. Enceladus, through its plume activity, is the source of this replenishment, single-handedly maintaining a planetary ring through its geological activity. It is a remarkable demonstration of how a small moon can have effects far beyond its own surface. The particles that make up the E-ring are predominantly water ice, matching the composition of Enceladus's plumes. They are extremely small, typically less than a micrometer in diameter, giving the ring its characteristic blue colour when viewed in scattered light. These particles are gradually pushed outward by the pressure of sunlight and inward by interactions with Saturn's magnetic field, spreading the ring over its enormous extent. Without Enceladus's continuous supply of fresh material, the E-ring would disappear within a few thousand years, a blink of an eye in geological terms. Beyond the tiger stripes, Enceladus's surface displays a variety of terrains that record the moon's complex geological history. The oldest regions are heavily cratered, their surfaces scarred by billions of years of impacts from asteroids and comets. These ancient terrains tell us that Enceladus formed early in solar system history, along with the other moons of Saturn, and has experienced the same bombardment that has affected all bodies in the outer solar system. But interspersed among these old, cratered regions are younger terrains that have been resurfaced by geological activity, their craters erased by flows of ice or covered by material erupted from below. The boundary between old and young terrains on Enceladus is often marked by systems of ridges and grooves, features that speak to the tectonic forces that have shaped the moon's surface. These ridges can rise several hundred meters above the surrounding terrain, while the grooves can be equally deep, creating a corrugated landscape unlike anything on Earth. The patterns of ridges and grooves vary across the moon, reflecting different stress regimes and different episodes of tectonic activity. In some places, they run parallel to each other in orderly ranks. In others, they intersect at various angles, creating complex networks that challenge scientists to interpret. The variety of surface features on Enceladus suggests that the moon has experienced multiple episodes of geological activity throughout its history, not just the current activity at the South Pole. Some scientists believe that the location of activity may have shifted over time, with different regions of the moon experiencing resurfacing at different epochs. The South Pole may simply be where activity happens to be occurring now, while other regions may have been active in the past and could become active again in the future. This idea of migrating activity adds another layer of complexity to our understanding of this dynamic little world. One of the most intriguing aspects of Enceladus's geology is the question of how long the current activity has been going on. The tiger stripes appear to be relatively young features, perhaps only a few million years old, based on the scarcity of impact craters on the south polar terrain. But the subsurface ocean may be much older, potentially having existed for billions of years if tidal heating has been continuous throughout the Moon's history. The relationship between the long-term presence of the ocean and the more recent opening of the tiger stripes is not fully understood and remains an active area of research. The discovery of Enceladus's ocean and plumes has profound implications for our understanding of where life might exist in the universe. For decades, scientists focused their search for extraterrestrial life on Mars, a world that once had liquid water on its surface and might still harbour life in underground aquifers. The discovery of subsurface oceans on icy moons like Enceladus and Europa has dramatically expanded the potential habitats for life, suggesting that liquid water might be common throughout the outer solar system and beyond. If life can arise in the dark, cold oceans of these distant moons, then the universe may be far more inhabited than we ever imagined. The case for habitability on Enceladus rests on several pillars. First and most fundamental is the presence of liquid water, the essential solvent for all life as we know it. Enceladus's ocean provides an enormous volume of liquid water that has apparently existed for a very long time, giving any potential life plenty of time to arise and evolve. Second is the presence of energy, both from tidal heating and from chemical reactions at hydrothermal vents. Life requires energy to power its metabolism, and Enceladus appears to have multiple energy sources available. Third is the presence of chemical nutrients, including the organic compounds detected in the plumes and the minerals dissolved in the ocean water. Life needs raw materials to build its structures and carry out its functions, and Enceladus seems to have these in abundance. The comparison to Earth's hydrothermal vents is particularly compelling. These underwater hot springs, found along mid-ocean ridges where tectonic plates are spreading apart, support thriving ecosystems entirely independent of sunlight. The base of the food chain at these vents consists of microorganisms that derive energy from chemical reactions, particularly the oxidation of hydrogen sulfide and other compounds emerging from the vents. These chemosynthetic bacteria support communities of tube worms, clams, shrimp, and other creatures that have adapted to the extreme conditions of the deep sea. If similar processes are occurring at the bottom of Enceladus's ocean, they could potentially support similar ecosystems, alien life forms thriving in the darkness beneath the ice. The discovery of phosphorus in Enceladus's plumes, announced in 2023 based on analysis of Cassini data, added another crucial piece to the habitability puzzle. Phosphorus is an essential element for life, as we know it, a key component of DNA, RNA, and the energy-carrying molecule ATP. Its presence in Enceladus's ocean means that all 6 of the elements most important for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are available in this distant world. The concentration of phosphorus detected was surprisingly high, perhaps 100 times higher than in Earth's oceans, suggesting that the chemical conditions in Enceladus's ocean may be even more favourable for life than those in our own planet's seas. Despite all these promising signs, we must be careful not to leap to conclusions about life on Enceladus. The presence of habitable conditions does not guarantee that life actually exists. It only means that life could potentially exist. The origin of life is still poorly understood, and we do not know how likely it is for life to arise even when conditions are favourable. It is possible that Enceladus has all the ingredients for life, but that the spark of life has never ignited there. It is also possible that life did arise but has since gone extinct, or that it exists but in forms so different from Earth life that we might not recognize it. Only direct exploration can answer these questions, and such exploration is now being actively planned. The search for life on Enceladus has a significant advantage over similar searches on other potentially habitable worlds. The plumes provide direct access to material from the subsurface ocean without the need to drill through kilometers of ice. A spacecraft flying through the plumes can sample ocean water that has been conveniently delivered to space, analyzing it for signs of life without ever landing on the surface. This accessibility makes Enceladus an exceptionally attractive target for astrobiology missions, and several concepts for such missions have been developed and proposed. One of the most detailed mission concepts is the Enceladus Orbilander, studied by NASA as a possible flagship mission for the 2030s or 2040s. This mission would first orbit Enceladus for several years, flying through the plumes multiple times to sample and analyze the ejected material. It would then land near one of the tiger stripes, using its instruments to study the surface ice and search for any biological material that might have been deposited by the plumes. The Orbilander would carry a sophisticated suite of life detection instruments, including mass spectrometers capable of identifying complex organic molecules, microscopes that could image individual cells, and chemical analyzers that could detect metabolic activity. Other proposed missions take different approaches to exploring Enceladus. Some concepts focus solely on plume sampling, using multiple flybys to gather material without the complexity and risk of landing. Others propose deploying small landers or even submarines that could melt through the ice and explore the ocean directly. Each approach has its advantages and challenges, and the eventual mission or missions that fly to Enceladus will depend on technological developments, scientific priorities, and funding availability. But the scientific community is united in viewing Enceladus as one of the highest priority targets for future exploration. While we await these future missions, scientists continue to analyze the wealth of data returned by Cassini during its 13 years at Saturn. New discoveries continue to emerge from this data, as researchers apply new analysis techniques and combine observations in novel ways. The Cassini mission may have ended in 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere to prevent any possibility of contaminating Enceladus or other potentially habitable moons. But its scientific legacy continues to grow. Each new paper published about Enceladus adds to our understanding of this remarkable world and sharpens the questions that future missions will seek to answer. Enceladus is not the only ocean world in the outer solar system, and understanding it helps us understand the broader category of such worlds. Jupiter's moon, Europa, has long been known to possess a subsurface ocean, revealed by the same kind of evidence that points to an ocean on Enceladus, a surface that appears to be floating on liquid magnetic field measurements, suggesting a conducting layer beneath the ice, and surface features that speak to geological activity. Europa's ocean is probably much larger than Enceladus's, contained within a moon that is itself much larger, and it too may have hydrothermal activity at its seafloor. The Europa Clipper mission, scheduled to arrive at Jupiter in 2030, will study this ocean world in unprecedented detail, conducting dozens of close flybys to map its surface, measure its ice shell thickness, and search for plumes similar to those on Enceladus. Europa presents both similarities and differences when compared to our small Saturnian moon. With a diameter of 322 kilometers, Europa is more than 6 times larger than Enceladus, making it roughly the size of Earth's moon. This greater size means Europa's ocean is correspondingly more vast, potentially containing 2 to 3 times as much water as all of Earth's oceans combined. The ice shell covering Europa's ocean is estimated to be between 15 and 25 kilometers thick, comparable to Enceladus's shell in some regions but potentially more uniform across the Moon's surface. Europa orbits Jupiter in just 3.5 Earth days, locked in an orbital resonance with the Moon's Io and Ganymede that generates the tidal heating responsible for maintaining its liquid ocean. The surface of Europa is one of the smoothest in the solar system, with very few impact craters marring its icy plains. This smoothness indicates that the surface is geologically young, constantly being renewed by processes from below. The most distinctive features on Europa are the lineae, long linear cracks that crisscross the surface in intricate patterns, some stretching for thousands of kilometers. These features are thought to form as Europa's ice shell flexes in response to tidal forces, cracking and refreezing in cycles that gradually build up the complex patterns we observe today. In some ways, the lineae are analogous to Enceladus's tiger stripes, though they appear to be less active and do not produce the dramatic plume activity seen at the south pole of our small moon. The question of whether Europa has plumes has been debated for years. The Hubble Space Telescope has occasionally detected what appear to be water vapour emissions near Europa's south pole, but these observations have been difficult to confirm, and the putative plumes seem to be sporadic rather than continuous like those on Enceladus. If Europa does have plumes, they are much less vigorous than Enceladus's jets, making them harder to detect and potentially harder to sample. This difference highlights one of Enceladus's great advantages as an astrobiology target. Its plumes are robust, continuous, and easily accessible to passing spacecraft, providing a window into the ocean below that Europa may not offer as readily. The composition of Europa's ocean remains less well characterized than Enceladus's, precisely because we lack the direct sampling that Cassini achieved at Saturn's small moon. Models suggest that Europa's ocean is likely salty, probably containing magnesium sulfate and other salts dissolved from the rocky seafloor. The ocean may be mildly acidic or mildly alkaline, depending on the specific chemical reactions occurring at the rock-water interface. Whether Europa has hydrothermal vents similar to those inferred on Enceladus is unknown but considered likely given the tidal heating the Moon experiences. The Europa Clipper mission will help constrain these questions, though direct sampling of any plume material would provide the most definitive answers. Beyond Europa, Jupiter's system contains 2 other moons that may harbour subsurface oceans. Ganymede, the largest moon in the solar system, shows evidence for a deep ocean sandwiched between layers of ice, trapped beneath perhaps 150 kilometres of frozen water. This ocean would be in contact with ice both above and below, rather than with rock, which might limit the chemical nutrients available for any potential life. Callisto, the outermost of Jupiter's large moons, may also possess a subsurface ocean, though the evidence is less certain than for Europa or Ganymede. The European Space Agency's JUICE mission, which launched in 2023 and will arrive at Jupiter in 2031, will study all 3 of these potentially ocean-bearing moons, with a particular focus on Ganymede, which it will eventually orbit. Returning to Saturn's system, Enceladus is not the only moon there with a potential subsurface ocean. Titan, Saturn's largest moon, is known to have a global ocean of liquid water beneath its icy crust, detected through measurements of how the moon's shape changes as it orbits Saturn. This ocean lies very deep, perhaps 50 to 100 kilometers below the surface, beneath a thick shell of water ice. Unlike Enceladus's ocean, Titan's subsurface water is not in direct contact with the surface or the atmosphere. The moon's famous hydrocarbon lakes and seas of liquid methane and ethane are entirely separate from the water ocean below. This separation makes Titan's water ocean much harder to access and study than Enceladus's ocean, which vents directly into space through the tiger-striped plumes. Titan deserves special mention because it is, in many ways, the most Earth-like world in the solar system, despite its frigid temperatures and exotic chemistry. It is the only moon with a substantial atmosphere, a thick blanket of nitrogen with traces of methane and other hydrocarbons that gives the moon its characteristic orange haze. On Titan's surface, liquid methane and ethane play the role that water plays on Earth, forming rivers, lakes and seas that cycle through the atmosphere as rain and evaporation. The Huygens probe, which descended through Titan's atmosphere in 2005, revealed a landscape of rounded pebbles and drainage channels eerily reminiscent of Earth despite being composed of water ice rather than rock and filled with hydrocarbons rather than water. The comparison between Enceladus and Titan illustrates the diversity of potentially habitable environments in the outer solar system. Enceladus offers a water ocean with hydrothermal energy and organic chemistry, conditions that closely parallel the environments where life may have originated on Earth. Titan offers a completely different kind of habitability, with its surface liquids and complex organic chemistry potentially supporting forms of life utterly unlike anything on Earth. Life that might use liquid methane as a solvent instead of water. Both moons are compelling targets for astrobiology, but they represent very different approaches to the question of life's possibilities. The discovery of ocean worlds has revolutionized our understanding of where life might exist in the universe. For most of the 20th century, scientists assumed that life required a planet in the habitable zone of its star, the narrow range of distances where liquid water could exist on a planet's surface. This assumption focused attention on Mars and on the search for Earth-like planets around other stars, while relegating the icy moons of the outer solar system to the category of frozen, lifeless worlds. The recognition that tidal heating can maintain liquid water oceans far from any star has shattered this assumption, revealing that habitable environments may be common throughout the cosmos, hidden beneath the icy surfaces of moons and dwarf planets far from the warmth of their parent stars. This expanded view of habitability has profound implications for the search for life beyond Earth. If life can arise in the subsurface oceans of icy moons, then such life might exist not just in our solar system, but throughout the galaxy, on moons orbiting giant planets, in systems where no Earth-like planet exists in the traditional habitable zone. Some scientists have suggested that ocean worlds might actually be the most common habitats for life in the universe, far outnumbering the relatively rare planets with liquid water on their surfaces. If this is true, then the universe may be teeming with life, but most of it may be hidden beneath ice, invisible to our telescopes and detectable only through close-up exploration. Enceladus occupies a special place among ocean worlds because of its accessibility. The plumes provide a direct sample of ocean material delivered conveniently to space, eliminating the need to land on the surface and drill through kilometers of ice. No other known ocean world offers this advantage. Europa may have plumes, but they are sporadic and weak compared to Enceladus's robust jets. Titan's ocean is buried far too deep to access without extraordinary engineering. Ganymede and Callisto show no signs of current geological activity that might provide access to their oceans. For a mission seeking to sample the ocean of another world and search for signs of life, Enceladus is the obvious choice, the one place where the ocean comes to us, rather than requiring us to go to it. The uniqueness of Enceladus's plumes raises interesting questions about why this small moon is so active while others are not. Part of the answer lies in the moon's size and composition. Enceladus is small enough that tidal heating can warm its entire interior, but large enough that it can retain an ocean rather than losing all its water to space. The moon's rocky core provides the minerals and chemical energy that make the ocean potentially habitable, and the particular configuration of Enceladus's orbit, locked in resonance with Dione, provides the continuous tidal flexing that maintains the heat source. Change any of these factors and Enceladus might be as dead and frozen as so many other small moons in the outer solar system. The comparison between Enceladus and Mimas is particularly instructive. Mimas is another moon of Saturn, similar in size to Enceladus and orbiting even closer to the planet, where tidal forces should be stronger. Yet Mimas shows no signs of geological activity, no plumes, no resurfaced terrain, nothing but a heavily cratered surface that has remained unchanged for billions of years. Why is Enceladus so active while Mimas is so dead? The answer may lie in the moon's different internal structures, with Enceladus having a more porous, easily heated interior, or in their different orbital histories, with Enceladus having experienced resonances that Mimas has not. Understanding this difference is important for predicting which moons in other planetary systems might be geologically active and potentially habitable. The study of ocean worlds has become one of the most dynamic fields in planetary science, driven by the discoveries at Enceladus and Europa and the promise of future exploration. Scientists are developing new models of how these oceans form and evolve, how tidal heating works in different configurations, and what chemical processes might occur at the interfaces between water and rock. Laboratory experiments simulate the conditions in these alien oceans, testing how organic molecules might form and survive, and how life might arise in such environments. Theoretical studies explore the possibilities for exotic forms of life that might thrive in conditions very different from those on Earth. All of this work is preparing us for the day when we can send spacecraft to these ocean worlds and search directly for signs of life. The implications of finding life on Enceladus or any other ocean world would be profound. Such a discovery would demonstrate that life is not unique to Earth, that the processes that gave rise to life here can occur elsewhere in the universe. If life arose independently on Enceladus, it would suggest that life is a common outcome of the right chemical conditions, that the universe may be filled with living worlds. Even if life on Enceladus turned out to be related to Earth life, perhaps carried there by meteorites blasted off our planet billions of years ago, it would still represent a second example of life, proof that biology can survive and thrive in environments very different from those where it originated. Either way, the discovery would transform our understanding of our place in the cosmos. As we contemplate these possibilities, Enceladus continues its eternal dance around Saturn, its plumes spraying continuously into the darkness of space, its hidden ocean churning with currents we can only imagine. This small moon, discovered more than 2 centuries ago as a tiny point of light in William Herschel's telescope, has become one of the most important objects in the solar system for understanding the potential for life beyond Earth. Its story is far from over. Indeed, the most exciting chapters may still lie ahead, waiting to be written by future missions and future discoveries. But for now, let us appreciate what we have learned. The remarkable journey of exploration that has revealed Enceladus to be a world of wonder, a place where fire and ice meet in the darkness, where an ocean hides beneath a frozen shell, where the conditions for life may exist in the most unexpected of places. Chapter 11. Future Exploration. Dreams of returning to Enceladus. The story of Enceladus exploration did not end with Cassini's final plunge into Saturn's atmosphere on September 15th, 2017. Even as that remarkable spacecraft was transmitting its last data, scientists and engineers were already dreaming of returning to this small moon, of following up on Cassini's discoveries with missions specifically designed to search for signs of life. These dreams have taken shape in numerous mission concepts, study reports, and proposals, each offering a different approach to the challenge of exploring Enceladus and its hidden ocean. While none of these missions has yet been approved for flight, the scientific community remains committed to returning to Enceladus, and the question is not whether we will go back, but when and how. The most straightforward approach to future Enceladus exploration is a dedicated plume sampling mission, a spacecraft designed specifically to fly through the jets and analyze the ejected material with instruments far more capable than those Cassini carried. Such a mission could determine the detailed composition of the ocean water, searching for complex organic molecules, potential biosignatures, and other indicators of habitability or life. The advantage of this approach is its relative simplicity. The spacecraft would not need to land or drill, merely to pass through the plumes at the right time and place, collecting samples as it flew. Several concepts for such missions have been studied, including the Enceladus Life Finder, which was proposed to NASA's Discovery program, and various international concepts that have been discussed but not yet funded. The challenge with plume sampling is ensuring that the spacecraft can collect enough material and analyze it thoroughly enough to detect signs of life if they are present. Cassini's instruments were designed for general planetary science, not specifically for astrobiology, and they had limited sensitivity for detecting complex organic molecules or other potential biosignatures. A dedicated life detection mission would need instruments capable of identifying amino acids, lipids, and other molecules associated with biology, distinguishing them from similar molecules that can form through non-biological processes. It would need to analyze the samples in multiple ways, using different techniques that could confirm or refute each other's findings. And it would need to collect samples from multiple plume passages, building up enough material to conduct thorough analyses. The Enceladus Orbilander concept, studied in detail by NASA's Planetary Science Decadal survey, takes the exploration a step further by combining orbital observations with a surface landing. The mission would begin with an orbital phase lasting several years, during which the spacecraft would fly through the plumes multiple times, mapping the surface in high resolution and characterizing the Moon's environment. After this orbital phase, the spacecraft would descend to the surface, landing near one of the tiger stripes, where plume material is deposited continuously. From the surface, it could study the ice in detail, analyzing samples that might contain material from the ocean below, and searching for any signs of biological activity. Landing on Enceladus presents significant challenges that must be overcome. The Moon's surface gravity is very low, only about 1% of Earth's gravity, which makes landing easier in some ways, but also means the spacecraft must be carefully designed to avoid bouncing or tipping over. The surface temperature is extremely cold, around -200 degrees Celsius, requiring robust thermal protection for the spacecraft's instruments and electronics. The terrain near the tiger stripes is rough and fractured, complicating the selection of a safe landing site, and the distance from Earth means that communications are delayed by over an hour each way, requiring the spacecraft to land autonomously without real-time guidance from mission controllers. Despite these challenges, the scientific payoff of a surface mission would be enormous. From the surface, instruments could analyze ice samples in ways that are impossible during a brief flyby, using techniques that require extended contact with the sample material. A lander could deploy a microscope to search for microbial cells or other structures that might indicate life. It could conduct chemical analyses over days or weeks, building up detailed profiles of the organic compounds present in the ice. It could measure the physical properties of the surface, determining how the plume material is deposited and modified over time. And it could monitor the plumes from below, observing how they change with Enceladus's orbital position and providing ground truth for orbital observations. Some mission concepts go even further, proposing to penetrate the ice shell and explore the ocean directly. These concepts are technically ambitious, requiring either a melt probe that would slowly descend through the ice by heating its way downward, or a drilling system capable of boring through kilometers of frozen water. Once in the ocean, a submarine or autonomous underwater vehicle could explore this alien sea, searching for hydrothermal vents, sampling the water at different depths, and looking for any signs of life in its native environment. Such missions remain in the realm of advanced concepts rather than near-term proposals, but they represent the ultimate goal of Enceladus exploration, direct access to the ocean that makes this moon so compelling. The technological requirements for subsurface exploration are daunting but not insurmountable. Melt probes have been tested in Earth's ice sheets, demonstrating that the basic concept works, though scaling up to the thickness of Enceladus's ice shell and operating in the harsh conditions of the outer solar system presents additional challenges. Communications through kilometers of ice would require either a tethered connection to the surface or acoustic systems capable of transmitting data through the frozen medium. Power for the probe would need to come from a nuclear source, as solar panels are useless beneath the ice, and chemical batteries cannot provide enough energy for a long-duration mission. And the probe would need to be thoroughly sterilized to prevent any Earth microbes from contaminating Enceladus's ocean, a requirement that adds complexity and cost to the mission. The question of planetary protection is particularly important for Enceladus exploration. Because the moon may harbour life, we must be extremely careful not to introduce Earth organisms that could contaminate the environment and confuse our search for native life. This means that any spacecraft sent to Enceladus must be thoroughly cleaned and sterilized, reducing the bioburden to levels low enough that contamination is extremely unlikely. For a surface lander or subsurface probe, the requirements are even more stringent, as these spacecraft would come into direct contact with the environment we are trying to study. The Cassini spacecraft was deliberately destroyed in Saturn's atmosphere, partly to ensure that it could never accidentally crash into Enceladus and potentially contaminate this pristine world. International cooperation may play an important role in future Enceladus exploration. The European Space Agency, the Japanese Space Agency JAXA, and other national space programs have all expressed interest in ocean world exploration, and collaborative missions could share the costs and technical challenges of reaching this distant moon. The success of the Cassini-Huygens mission, a collaboration between NASA and ESA, demonstrates that international partnerships can produce outstanding scientific results in the outer solar system. Future missions to Enceladus might follow a similar model, combining the resources and expertise of multiple space agencies to accomplish what no single agency could achieve alone. The timeline for returning to Enceladus remains uncertain, dependent on funding decisions, technological developments, and scientific priorities. The most recent Planetary Science Decadal Survey, which sets priorities for NASA's planetary exploration program, ranked Enceladus highly as a target for future exploration, but did not recommend an immediate flagship mission, instead calling for further technology development and smaller precursor missions. The Europa Clipper mission, currently under development and scheduled to launch in 2024, will demonstrate many of the technologies needed for ocean world exploration, including ice-penetrating radar, mass spectrometers for analyzing plume material, and radiation-hardened electronics for operating in harsh environments. Lessons learned from Europa Clipper will inform the design of future Enceladus missions. In the meantime, scientists continue to advocate for Enceladus exploration, publishing papers that highlight the moon's astrobiological potential and developing mission concepts that could be proposed when opportunities arise. The scientific case for returning to Enceladus is strong and growing stronger as we continue to analyze Cassini data and develop our understanding of ocean world habitability. The question of whether life exists beyond Earth is one of the most profound questions humanity can ask, and Enceladus offers perhaps our best chance of answering it within our lifetimes. The plumes are there, waiting to be sampled. The ocean is there, waiting to be explored, and somewhere in that dark, cold water, life may be waiting to be discovered. The development of new technologies continues to expand what future missions might accomplish. Advances in miniaturization allow more capable instruments to be packed into smaller spacecraft, reducing launch costs and enabling more ambitious missions. New propulsion systems, including solar electric propulsion and advanced chemical rockets, can deliver spacecraft to the outer solar system more quickly and with more fuel for maneuvering once they arrive. Improved autonomous navigation systems allow spacecraft to operate independently for extended periods, essential for missions to distant worlds where communication delays make real-time control impossible. And advances in sample handling and analysis techniques make it possible to detect ever smaller quantities of potential biosignatures, increasing the chances of finding life if it exists. The private space industry may also play a role in future Enceladus exploration. Companies like SpaceX are developing heavy-lift rockets that could send larger payloads to the outer solar system than current vehicles allow, potentially enabling more ambitious missions at lower cost. Other companies are developing technologies for in-space manufacturing and resource utilization that could eventually support sustained exploration of the outer solar system. While private missions to Enceladus remain speculative, the rapid pace of innovation in the commercial space sector suggests that new possibilities may emerge in the coming decades. As we look toward the future of Enceladus exploration, it is worth reflecting on how far we have come. Just a few decades ago, Enceladus was a tiny, mysterious point of light, one of dozens of small moons orbiting Saturn with no particular distinction. Today, it is recognized as one of the most important objects in the solar system, a world that may harbor the conditions for life and that offers our best opportunity to search for that life directly. This transformation is a testament to the power of exploration, to the ability of spacecraft and instruments to reveal wonders that we could never have imagined from Earth. Whatever the future holds, the story of Enceladus exploration is one of humanity's great scientific adventures, a journey of discovery that is still unfolding. The dreams of future exploration are not merely technical exercises. They represent our deepest aspirations as a species. We explore because we are curious, because we want to understand our place in the universe, because we hope to find that we are not alone. Enceladus embodies these aspirations perhaps more than any other world, offering the tantalizing possibility that life might exist in the most unexpected of places, that the universe might be more alive than we ever dared to hope. When we finally return to this small moon, when we sample its plumes and analyze its ice and perhaps one day explore its ocean, we will be seeking answers to questions that have haunted humanity since we first looked up at the stars and wondered what might be out there. Chapter 12. Cosmic Perspective Reflections on a Small Moon's Big Story. As our journey through the story of Enceladus draws toward its close, let us take a moment to step back and consider what this small moon means in the grander context of our exploration of the cosmos. Enceladus is, by any measure, a tiny world, just 500 kilometers across, small enough to fit within the borders of a medium-sized country on Earth. It orbits a planet nearly 1.5 billion kilometers from the Sun, in a region of the solar system so cold that water exists only as rock-hard ice on any surface exposed to space. By all rights, Enceladus should be a frozen, dead world, a leftover fragment from the formation of the solar system with nothing to offer but a record of ancient impacts. Yet this small moon has proven to be one of the most dynamic and potentially habitable places we have ever discovered. A reminder that the universe is full of surprises and that we should never assume we know what lies waiting to be found. The story of Enceladus is, in many ways, the story of scientific discovery itself. It begins with a point of light in a telescope, a faint glimmer that William Herschel noticed moving against the background of stars on a summer night in 1789. It continues through centuries of patient observation as astronomers gradually piece together the basic facts about this distant moon, its size, its orbit, its exceptional brightness. It accelerates with the space age as the Voyager spacecraft provided our first close-up views and revealed hints of geological activity that defied explanation. And it culminates with Cassini, the mission that transformed Enceladus from a curiosity into a world, revealing its plumes, its ocean, its tiger stripes, and its potential for life. Each stage of this story has been marked by surprises, by discoveries that overturned assumptions and opened new questions. When Herschel found Enceladus, no one imagined that such a small moon could be geologically active. The very concept of geological activity on icy moons had not yet been conceived. When Voyager revealed the smooth plains and fractured terrain, scientists struggled to explain how such a small world could resurface itself. The mechanisms of tidal heating in icy moons were still poorly understood. When Cassini discovered the plumes, the scientific community was astonished. No one had predicted that Enceladus would be actively venting material into space. And when subsequent analysis revealed the subsurface ocean and its potential habitability, Enceladus leaped from an interesting geological puzzle to one of the most important targets in the search for life beyond Earth. This pattern of surprise and discovery is not unique to Enceladus. It characterizes the entire history of planetary exploration. Again and again, spacecraft have revealed worlds that defied our expectations, that were more complex, more dynamic, more interesting than we had imagined. Mars turned out to have had rivers and lakes in its ancient past. Venus proved to be a hellish world of crushing pressure and scorching temperatures, not the tropical paradise some had imagined. Jupiter's moon. Io was discovered to be the most volcanically active body in the solar system, its surface constantly renewed by eruptions of sulfur and silicate lava. Titan revealed itself to be a world with weather and seasons, with rain and rivers and lakes, albeit composed of hydrocarbons rather than water. Each of these discoveries expanded our understanding of what is possible in the universe, of the range of conditions that can exist on other worlds. Enceladus fits into this pattern while also standing apart from it. Like other surprising worlds, it has revealed unexpected activity and complexity, challenging our assumptions about what small cold moons can do. But Enceladus is special because of what its activity implies: the existence of a habitable environment, a place where life might exist. This possibility elevates Enceladus from a geological curiosity to an astrobiological priority, a world that might help us answer one of the most profound questions we can ask. Are we alone in the universe? The question of life beyond Earth has fascinated humanity for as long as we have known that other worlds exist. Ancient philosophers speculated about inhabitants of the moon and planets. Early astronomers searched for signs of civilization on Mars, imagining canals and cities on the red planet's surface. The 20th century brought the sobering realization that the other planets in our solar system are not home to advanced civilizations, but also the exciting discovery that the conditions for life might exist in unexpected places. The search for extraterrestrial life has evolved from speculation to science, from imagination to investigation, and Enceladus represents one of the most promising targets in this ongoing search. If life exists on Enceladus, it would almost certainly be microbial, simple single-celled organisms, similar to the bacteria and archaea that dominate Earth's biosphere. Such organisms would likely live in the ocean, perhaps clustered around hydrothermal vents, where chemical energy is abundant, perhaps drifting freely in the water column, perhaps clinging to the underside of the ice shell. They would be adapted to conditions very different from those on Earth's surface, thriving in cold, dark, high-pressure environments with no sunlight and limited nutrients. But they would be life nonetheless, fellow travellers in the cosmos, proof that the spark of life can ignite in more than one place. The discovery of such life would transform our understanding of the universe and our place in it. For all of human history, we have known only one example of life, the interconnected web of organisms that share our planet, all descended from a common ancestor that arose billions of years ago. This single example tells us that life is possible, but it cannot tell us how likely life is to arise, how common it might be in the universe, or what forms it might take. A second example of life, especially one that arose independently from Earth life, would provide crucial data for answering these questions. It would suggest that life is not a fluke, not a one-time accident, but a natural outcome of the right conditions, something that the universe produces readily when the ingredients are present. Even if Enceladus proves to be lifeless, the search will have been worthwhile. Understanding why life did not arise in an apparently habitable environment would teach us something important about the conditions required for life, about the factors that tip the balance from chemistry to biology, and the exploration of Enceladus would still yield invaluable scientific knowledge about ocean worlds, tidal heating, ice shell dynamics, and the chemistry of water-rock interactions. Every mission to another world expands our understanding of the solar system and the universe, regardless of whether it finds life. The search itself is the reward, the journey of discovery that defines us as a curious and exploring species. As you lie there, perhaps feeling the gentle pull of sleep beginning to settle over you, consider the remarkable chain of events that connects you to that small moon orbiting Saturn. The atoms in your body were forged in ancient stars, scattered across the galaxy by supernova explosions, gathered together by gravity into the cloud of gas and dust that became our solar system. The same processes that formed Earth also formed Enceladus, the same elements combining in different proportions and different conditions to create worlds as different as our blue planet and that small icy moon. We are made of the same stuff as Enceladus, connected to it by the shared history of our solar system, and when we send spacecraft to explore that distant world, we are in a sense exploring a part of our own cosmic heritage. The universe is vast beyond comprehension, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars orbited by planets and moons of their own. In this immense cosmos, Earth is a tiny speck, a pale blue dot suspended in a sunbeam, as Carl Sagan so memorably described it. And yet from this tiny speck, we have reached out to explore our cosmic neighbourhood, sending our robotic emissaries to every planet in the solar system and beyond. We have walked on the Moon, landed on Mars, orbited Jupiter and Saturn, and even sent spacecraft to the edge of interstellar space. Enceladus is part of this great adventure, one destination among many in humanity's ongoing exploration of the cosmos. The story of Enceladus also reminds us of the importance of patience and persistence in scientific exploration. More than 2 centuries passed between Herschel's discovery and Cassini's revelation of the plumes, 2 centuries during which Enceladus remained a mystery, its secrets hidden by distance and the limitations of our technology. The scientists who planned the Cassini mission could not have known what they would find at Enceladus. They included the Moon in the mission's itinerary because it was there, because exploring Saturn's system meant exploring all of its moons, not because they expected to find anything particularly remarkable. The discovery of the plumes was a surprise, a gift from the universe to those patient enough to go and look. This lesson applies to all of science and, indeed, to all of life. We cannot always predict where discoveries will come from, which experiments will yield breakthroughs, which observations will reveal new truths. We can only keep looking, keep asking questions, keep exploring with open minds and curious hearts. Enceladus teaches us that wonders await in unexpected places, that the universe is more interesting than we imagine, and that the rewards of exploration are worth the effort and expense required to achieve them. As the night deepens and sleep approaches, let your mind drift among the stars, out past Mars and Jupiter, through the asteroid belt and onward to Saturn with its glorious rings. Imagine yourself approaching Enceladus, watching as that small bright moon grows larger in your view, its surface gleaming with the reflected sunlight, its south pole wreathed in the delicate spray of its plumes. Imagine descending through those plumes, feeling the tiny ice particles brush past you, each one a sample of the ocean below, a message from a hidden world. Imagine sinking beneath the ice, into the darkness of the ocean, where no sunlight has ever penetrated, where the only light comes from the glow of hydrothermal vents on the seafloor below. In that darkness, in that cold and pressure and isolation, life might exist. Simple organisms, perhaps, bacteria-like creatures going about their microscopic lives, unaware of the vast universe beyond their frozen ceiling, unaware that curious beings on a distant world are dreaming of finding them. Or perhaps the ocean is sterile, a vast body of water with all the ingredients for life, but missing some crucial spark, some essential catalyst that would transform chemistry into biology. We do not know which possibility is true, and we may not know for decades until we can send spacecraft capable of answering the question. But the not knowing is part of what makes Enceladus so compelling, the mystery that draws us onward, the question that demands an answer. The exploration of Enceladus is part of a larger human story, the story of our species reaching out beyond our home world to understand the universe we inhabit. This story began when our ancestors first looked up at the night sky and wondered about the lights they saw there. It continued through millennia of observation and speculation, through the invention of the telescope and the development of modern science, through the space age and the robotic exploration of the solar system. It continues today as scientists analyze Cassini data and plan future missions, as engineers develop new technologies for reaching distant worlds, as dreamers imagine what we might find when we finally return to Enceladus. You are part of this story, connected to it by your curiosity, by your interest in learning about worlds beyond our own, by your willingness to spend this time exploring the story of a small moon orbiting a distant planet. Every person who learns about Enceladus, who marvels at its plumes and wonders about its ocean, who hopes that we might find life there, is participating in humanity's great adventure of exploration. You do not need to be a scientist or an astronaut to be part of this story. You need only to care, to wonder, to dream. And so, as sleep begins to claim you, carry with you the image of Enceladus, that small bright moon with its hidden ocean and its spraying plumes. Let it remind you that the universe is full of wonders, that there is always more to discover, that the questions we ask today may be answered by the explorers of tomorrow. Let it inspire you to look up at the night sky with fresh eyes, knowing that among those distant points of light are worlds we have visited, worlds we have studied, worlds that have revealed themselves to be far more interesting than anyone could have predicted. The plumes of Enceladus continue their eternal dance even as you rest, spraying water and ice particles high above the moon's south pole, feeding Saturn's E-ring with fresh material, carrying samples of the hidden ocean into the vacuum of space. Those plumes have been active for perhaps millions of years, perhaps longer, a continuous fountain of material that speaks to the dynamic processes occurring within this small world. They will likely continue for millions of years more, long after our brief human lives have ended, long after the civilizations we build have risen and fallen, long after our descendants have spread across the solar system and perhaps beyond. Enceladus is patient, as all worlds are patient, operating on timescales that dwarf our human concerns, yet offering itself to our study whenever we choose to look. The James Webb Space Telescope, humanity's newest and most powerful eye on the universe, has already turned its gaze toward Enceladus, revealing the plumes in unprecedented detail. In observations conducted in late 2022, Webb detected a water vapor plume extending an astonishing 9,600 kilometers from the moon's surface, a spray of material reaching 20 times the diameter of Enceladus itself. This enormous plume, far larger than anything Cassini had observed, demonstrates that the moon's activity continues unabated and may even be more vigorous than we previously understood. The Webb observations also allowed scientists to trace how the ejected water spreads through space, forming a torus of material around Saturn that gradually disperses into the broader environment. These new observations remind us that our understanding of Enceladus is still evolving, still being refined by new data and new perspectives. Each time we look at this small moon with better instruments or from different vantage points, we learn something new, something that adds to the picture we have been building since Herschel's first glimpse in 1789. The story of Enceladus is not a finished tale, but an ongoing narrative, one that will continue to unfold as long as humans remain curious about the worlds beyond our own. Consider for a moment the sheer improbability of our knowing anything at all about Enceladus. This small moon orbits a planet nearly 1.5 billion kilometers from Earth, a distance so vast that light itself takes over an hour to make the journey. The moon is tiny, just 500 kilometers across, a speck against the immensity of space. Its surface temperature hovers around -201 degrees Celsius, cold enough to freeze any unprotected human solid in moments. And yet, through the accumulated efforts of thousands of scientists, engineers, and dreamers over more than 2 centuries, we have come to know this distant world intimately, to understand its geology and chemistry, to map its surface and probe its interior, to sample its plumes and analyze its ocean water. This knowledge represents one of humanity's greatest achievements, a triumph of curiosity and ingenuity over the vast distances and harsh conditions that separate us from other worlds. Every fact we know about Enceladus was hard-won. extracted from faint signals travelling across the solar system, interpreted through careful analysis and creative thinking, tested against alternative explanations until only the truth remained. The scientists who study Enceladus are explorers in the truest sense, venturing into unknown territory, not with their bodies but with their minds, using instruments and mathematics to reveal what direct experience cannot reach. As you drift deeper into relaxation, let your breathing slow and your thoughts gentle. Imagine the quiet of space around Enceladus, the profound silence of a world without air, without wind, without the constant background noise that fills our earthly lives. In that silence, the plumes rise and fall in response to tidal forces. The ice shell flexes and cracks. The ocean currents flow in patterns we can only imagine. Life, if it exists there, goes about its business in the darkness, unaware of the distant world where curious beings dream of finding it. The ocean beneath Enceladus's ice is a place of perpetual night, a realm where sunlight has never penetrated, where the only illumination might come from the faint glow of hydrothermal vents or the bioluminescence of organisms, if any exist. This ocean has been isolated from the surface for millions or billions of years, evolving its own chemistry, its own conditions, its own potential for life. It is a world within a world, a hidden realm that we have only begun to glimpse through the samples carried up by the plumes. The chemistry of this ocean is remarkably Earth-like in some ways, remarkably alien in others. The water is salty, containing sodium chloride and other dissolved minerals that speak to long interaction with the rocky core below. The pH is mildly alkaline, similar to soapy water, creating conditions that many Earth organisms would find hospitable. Organic molecules are present, the carbon-based compounds that form the building blocks of life as we know it, and molecular hydrogen, produced by reactions between hot water and rock, provides a potential energy source for any organisms that might call this ocean home. Yet this ocean is also profoundly different from Earth's seas. It exists under kilometres of ice, isolated from the atmosphere and from any input of solar energy. Its temperatures range from near freezing in the bulk of the water to perhaps quite warm near hydrothermal vents on the seafloor. The pressure at the bottom of the ocean, where water meets rock, is substantial, though not as extreme as in Earth's deepest trenches, and the ocean has been evolving in isolation for an immense span of time, potentially developing chemistry and conditions unlike anything we have experienced on our own world. If life exists in this ocean, it would have arisen and evolved under conditions very different from those that shaped life on Earth. It might use different biochemistry, different energy sources, different strategies for survival and reproduction. It might be recognizable as life, with cells and metabolism and reproduction, or it might be so different that we would struggle to identify it as living at all. The search for life on Enceladus is not just a search for familiar organisms in an unfamiliar place. It is a search for the very boundaries of what life can be, for the range of possibilities that the universe allows. Some scientists have raised intriguing questions about the source of the plumes, suggesting that the water might not come directly from the deep ocean but from pockets of liquid within the ice shell itself. These pockets, sometimes called mush zones, would form where tidal heating melts portions of the ice, creating reservoirs of water that could feed the plumes without requiring a direct connection to the ocean below. If this is the case, the plume material might not be fully representative of the ocean's composition, and our inferences about the ocean's chemistry and habitability might need to be revised. This uncertainty is a reminder that science is a process of continuous refinement, of testing hypotheses against evidence and revising our understanding when the evidence demands it. The discovery of the plumes was a surprise, The inference of a subsurface ocean was a conclusion drawn from multiple lines of evidence, and the possibility that the plumes might sample something other than the deep ocean is a new hypothesis that must be tested by future observations and missions. Each step in this process brings us closer to the truth, even when that truth turns out to be more complicated than we initially assumed. The question of whether the plumes come directly from the ocean or from shallower reservoirs has important implications for the search for life. If the plumes sample the deep ocean directly, then any biosignatures present in the ocean should be detectable in the plume material, making the search for life relatively straightforward. If the plumes come from isolated pockets within the ice, then those pockets might have different chemistry and different potential for life than the ocean below, and sampling the plumes might not tell us what we most want to know about the ocean's habitability. Future missions will need to address this question, perhaps by sampling plumes from different vents or at different times, or by using ice-penetrating radar to map the structure of the ice shell and identify any subsurface reservoirs. Despite these uncertainties, the fundamental picture of Enceladus as an ocean world with potential for life remains robust. Multiple independent lines of evidence point to a global liquid water ocean beneath the ice shell. The chemistry of the plumes indicates conditions that could support life as we know it, and the presence of hydrothermal activity suggests that energy is available to power biological processes. Whether the plumes sample the ocean directly or through intermediate reservoirs, the basic conclusion that Enceladus is a habitable world remains sound. As your thoughts continue to drift and your body relaxes more deeply, consider the profound questions that Enceladus raises about our place in the universe. Are we alone? Is Earth the only world where life has taken hold, or is life a common phenomenon, arising wherever conditions permit? These questions have been asked for centuries, but only now do we have the tools to begin answering them. Enceladus, with its accessible ocean and its spraying plumes, offers perhaps our best opportunity to find that answer within our lifetimes. The search for life beyond Earth is not just a scientific endeavour, it is a deeply human quest rooted in our desire to understand ourselves and our place in the cosmos. If we find life on Enceladus, it will change how we think about the universe and our relationship to it. We will know that we are not alone, that life is not unique to our small planet, that the universe is more alive than we ever dared to hope. And if we search and find nothing, we will have learned something important too, that life is rare, that Earth is precious, that we bear a special responsibility to protect the only world we know for certain harbours life. Either way, the search is worth undertaking. The exploration of Enceladus, like all exploration, expands our horizons and deepens our understanding. It challenges us to develop new technologies, to ask new questions, to push beyond the boundaries of what we know. It connects us to something larger than ourselves, to the grand adventure of discovery that has driven humanity since our ancestors first wondered about the lights in the sky. Chapter 13. The Poetry of Ice and Water, Enceladus in Human Imagination. Beyond the scientific facts and figures, Enceladus has captured something deeper in the human imagination, a sense of wonder and possibility that transcends the data returned by spacecraft. This small moon has become a symbol of the unexpected, a reminder that the universe is more creative and more surprising than our theories predict. In the decades since Cassini revealed its secrets, Enceladus has inspired artists, writers, musicians, and dreamers, becoming part of our cultural landscape as well as our scientific understanding. The image of the plumes, those graceful fountains of ice and vapour rising from the tiger stripes, has become iconic, reproduced in countless articles, documentaries, and educational materials. There is something inherently beautiful about these features, something that speaks to us on an aesthetic level as well as an intellectual one. The plumes are delicate yet powerful, ephemeral yet persistent, rising from a world of ice into the vacuum of space in a display that seems almost designed to capture our attention. They are nature's way of announcing that this small moon is special, that something remarkable is happening beneath its frozen surface. The tiger stripes themselves have a poetic quality, their parallel lines cutting across the south polar terrain like the marks of some cosmic calligrapher. Their names, drawn from the cities of the Arabian Nights, add to their mystique: Alexandria, Cairo, Baghdad, Damascus. These names connect Enceladus to human history and culture, to the ancient stories of wonder and adventure that have been told around campfires and in palace halls for thousands of years. The scientists who named these features understood that exploration is not just about data and measurements. It is about meaning and connection, about weaving new discoveries into the fabric of human experience. The concept of a hidden ocean has particular resonance in human culture. Throughout history, we have been fascinated by the idea of worlds beneath the surface, of realms hidden from view where strange creatures might dwell. From the underground rivers of mythology to the submarine adventures of Jules Verne, from the hollow earth theories of the 19th century to the deep-sea documentaries of today, we have always been drawn to the idea of hidden waters and the life they might contain. Enceladus's ocean taps into this deep fascination, offering a real-world example of a hidden sea that might harbour life, a place where our imagination and our science converge. The possibility of life on Enceladus has inspired countless works of fiction, from hard science fiction that hews closely to what we know, to more speculative tales that imagine what we might find. Writers have populated Enceladus's ocean with everything from simple microbes to complex ecosystems, from familiar-looking fish to utterly alien creatures that challenge our definitions of life. These stories serve an important function, allowing us to explore the implications of discovery before the discovery is made, to rehearse our reactions and consider our responsibilities. Fiction is a laboratory for the imagination, and Enceladus has become one of its most productive subjects. The moon has also inspired visual artists who have created stunning depictions of its surface, its plumes, and its hidden ocean. Some of these works are based closely on Cassini imagery, translating the spacecraft's data into paintings and digital art that capture the beauty of this distant world. Others are more imaginative, depicting scenes that no spacecraft has yet witnessed. The view from beneath the ice, the glow of hydrothermal vents on the seafloor, the hypothetical creatures that might swim in the darkness. These artistic interpretations help us connect emotionally to a world we can never visit in person, making the abstract concrete and the distant intimate. Musicians too have found inspiration in Enceladus, composing pieces that evoke the moon's icy beauty and mysterious depths. Some of these compositions use data from Cassini as their raw material, translating measurements of magnetic fields or particle densities into sound, creating music that is literally derived from the moon itself. Others take a more traditional approach, using conventional instruments and compositional techniques to capture the mood and atmosphere of this distant world. Whether data-driven or purely imaginative, these musical works add another dimension to our experience of Enceladus, engaging our sense of hearing as well as our sense of sight. The cultural impact of Enceladus extends beyond the arts to education and public engagement with science. The moon has become a favourite subject for science communicators, who use its story to illustrate the excitement and importance of planetary exploration. Documentaries about Enceladus have reached millions of viewers, introducing them to the wonders of the outer solar system and the possibility of life beyond Earth. Educational materials about the Moon are used in classrooms around the world, inspiring the next generation of scientists and explorers. Enceladus has become a gateway to the cosmos, a compelling example that draws people into the broader story of space exploration. The naming of features on Enceladus reflects the international and multicultural nature of modern space exploration. While the tiger stripes bear names from Arabian tradition, other features on the Moon are named after characters and places from the tales of Sir Richard Burton, the 19th century explorer and translator who brought the Arabian Nights to English-speaking audiences. This naming scheme connects Enceladus to a rich tradition of storytelling and exploration, reminding us that the quest to understand distant worlds is part of a longer human journey that spans cultures and centuries. As you rest and your mind wanders, consider how Enceladus has become part of our shared human heritage, a world that belongs to all of us, regardless of nationality or background. The spacecraft that explored it were built by international teams, funded by taxpayers from multiple countries, operated by scientists from around the world. The data returned by these missions is freely available to anyone who wishes to study it, a gift from the explorers to all of humanity. And the discoveries made at Enceladus belong to everyone, expanding our collective understanding of the universe we inhabit. This shared ownership of discovery is one of the most beautiful aspects of space exploration. Unlike so many human endeavours, which divide us into competing groups and nations, the exploration of other worlds unites us in a common purpose. When Cassini discovered the plumes of Enceladus, it was not an American discovery or a European discovery. It was a human discovery, a moment when our species as a whole learned something new about the cosmos. The scientist who made the discovery came from many countries and backgrounds, working together across borders and boundaries to achieve something none could have accomplished alone. The story of Enceladus is thus not just a story about a moon, it is a story about us, about what we can achieve when we work together, about the heights we can reach when we set aside our differences and pursue a common goal. It is a story of curiosity and perseverance, of patience and ingenuity, of the human spirit reaching out across the vastness of space to touch another world. And it is a story that is still being written, with new chapters waiting to be added by future missions and future discoveries. Chapter 14. The Rhythm of Tides, Understanding Enceladus's Heartbeat. To truly appreciate Enceladus, we must understand the forces that make it what it is, the gravitational rhythms that pulse through this small moon and drive its remarkable activity. At the heart of Enceladus's story is tidal heating, the process by which gravitational interactions with Saturn and other moons generate the heat that maintains the subsurface ocean and powers the plumes. This process is Enceladus's heartbeat, the steady pulse of energy that keeps this small world alive in the cold darkness of the outer solar system. Tidal heating occurs because Enceladus does not orbit Saturn in a perfect circle. Its orbit is slightly elliptical, meaning that the moon's distance from Saturn varies as it travels around the planet. When Enceladus is closer to Saturn, the planet's gravitational pull is stronger. When it is farther away, the pull is weaker. This variation in gravitational force causes Enceladus to flex and stretch as it orbits, its shape changing slightly in response to the changing tidal forces. This flexing generates friction within the moon's interior, and friction generates heat. The amount of heat generated by tidal flexing depends on several factors, including the eccentricity of the orbit, the size and composition of the moon, and the properties of its interior. For Enceladus, the orbital eccentricity is maintained by a gravitational resonance with Dione, another of Saturn's moons. For every orbit Dione completes around Saturn, Enceladus completes exactly 2. This resonance prevents Enceladus's orbit from becoming perfectly circular, ensuring that tidal heating continues indefinitely. Without this resonance, Enceladus's orbit would gradually circularize, tidal heating would cease, and the moon would freeze solid. The heat generated by tidal flexing is not distributed evenly throughout Enceladus. Instead, it appears to be concentrated in certain regions, particularly the south polar area where the tiger stripes are located. Scientists are still working to understand why the heating is so localized, but the concentration of activity at the South Pole suggests that something about the moon's internal structure or the pattern of tidal stresses focuses the heat in this region. The result is a hot spot at the South Pole, a region where the ice shell is thin, the ocean is close to the surface, and material can escape through the tiger stripe fractures. The tiger stripes themselves respond to tidal forces in a rhythmic pattern that has been observed by Cassini. As Enceladus moves through its orbit, the tidal stresses on the ice shell change, causing the tiger stripe fractures to open and close like slowly breathing wounds. When the fractures are open, material from below can escape more easily, and the plumes are more vigorous. When the fractures close, the flow is reduced. This tidal pumping creates a regular variation in plume activity that correlates with Enceladus's orbital position, a heartbeat that pulses with each 33-hour orbit around Saturn. The relationship between tidal heating and the subsurface ocean is complex and not fully understood. The ocean acts as a buffer, absorbing heat from below and distributing it throughout the moon's interior. It also lubricates the ice shell, allowing it to flex more easily in response to tidal forces and potentially enhancing the amount of heat generated. The ice shell, in turn, insulates the ocean, preventing it from freezing solid despite the extreme cold of the surrounding environment. This interplay between ocean ice and tidal heating creates a self-sustaining system that has apparently maintained liquid water on Enceladus for millions or billions of years. The energy budget of Enceladus has been a subject of considerable scientific debate. Early estimates of the heat flow from the South Polar region, based on Cassini's infrared observations, suggested that Enceladus was producing more heat than could be easily explained by tidal heating alone. This discrepancy led to various hypotheses, including the possibility that Enceladus's internal structure is different from what models assumed, or that the moon is currently in a particularly active phase that will eventually subside. More recent analyses have revised the heat flow estimates and improved the tidal heating models, bringing them into better agreement. But questions remain about the long-term stability of Enceladus's activity. One intriguing possibility is that Enceladus's activity is episodic, with periods of intense heating and plume activity alternating with quieter phases. In this scenario, the current activity at the South Pole might be a relatively recent development, perhaps triggered by some change in the moon's internal structure or orbital dynamics. The tiger stripes might have opened only a few million years ago, initiating the current phase of plume activity, and they might eventually close again as conditions change. This episodic model could help explain some of the puzzling aspects of Enceladus's geology, including the presence of both ancient cratered terrain and young resurfaced regions. The study of tidal heating on Enceladus has broader implications for understanding icy moons throughout the solar system and beyond. The same basic process that powers Enceladus's activity also operates on Europa, Ganymede, and other moons with subsurface oceans. By studying how tidal heating works on Enceladus, scientists can develop better models that apply to these other worlds, predicting which moons might be geologically active and which might harbour habitable environments. This knowledge is essential for planning future exploration missions and for understanding the potential for life in the outer solar system. The tidal forces that heat Enceladus also shape its surface in ways that go beyond the tiger stripes. The moon's ice shell is crisscrossed by fractures and ridges that record the history of tidal stresses, a frozen record of the forces that have acted on the moon over millions of years. By studying these features, scientists can reconstruct the history of tidal heating on Enceladus, determining how the pattern of stresses has changed over time and how the moon's activity has evolved. This geological detective work is painstaking but rewarding, revealing the dynamic history of a world that might otherwise seem static and unchanging. As you continue to relax, imagine the gentle rhythm of Enceladus's tides, the slow flexing of ice and rock as the moon orbits Saturn, the pulse of heat that keeps the ocean liquid and the plumes flowing. This rhythm has continued for eons, a cosmic heartbeat that marks the passage of time in the outer solar system. It will continue for eons more, long after we are gone, a testament to the enduring power of gravity and the remarkable ways that energy can flow through the universe. Chapter 15. Whispers from the Deep. What the plumes tell us. The plumes of Enceladus are more than just a spectacular display. They are messengers from the deep, carrying information about the hidden ocean to the surface and beyond. Every ice particle, every molecule of gas that escapes through the tiger stripes is a sample of the world below, a whisper from the deep that scientists have learned to interpret. Through careful analysis of the plume material, we have gained insights into the ocean's composition, temperature, and potential for life that would otherwise be impossible to obtain without drilling through kilometres of ice. The plumes consist primarily of water vapour, the gaseous form of the water that makes up the ocean below. This vapour escapes through the tiger stripe fractures, driven by the pressure difference between the warm interior and the vacuum of space. As the vapour rises, it cools rapidly, and some of it condenses into tiny ice particles that are carried along with the gas. These particles range in size from nanometers to micrometers, small enough to be lofted high above the surface, but large enough to be detected and analysed by spacecraft instruments. Mixed with the water vapour and ice are a variety of other compounds that provide clues to the ocean's chemistry. Cassini detected sodium chloride in the plume particles, the same salt that makes Earth's oceans taste salty, indicating that Enceladus's ocean has been in contact with rock and has dissolved minerals over time. Sodium carbonate and sodium bicarbonate were also found, suggesting alkaline conditions in the ocean. These salts are not present in the vapour phase, but are concentrated in the ice particles, which appear to form from liquid water droplets that freeze as they rise through the fractures. The detection of organic molecules in the plumes was one of Cassini's most exciting discoveries. The spacecraft found a variety of carbon-containing compounds, including simple molecules like methane, propane, acetylene, and formaldehyde. More remarkably, later analysis revealed the presence of large complex organic molecules with masses suggesting they contain hundreds of atoms. These molecules are too large to have formed in the plumes themselves. They must have originated in the ocean, where chemical reactions have been building up complex organic chemistry over millions or billions of years. The presence of molecular hydrogen in the plumes was another crucial finding, announced in 2017 based on Cassini data. Hydrogen gas is produced when water reacts with certain types of rock at high temperatures, a process called serpentinization that occurs at hydrothermal vents on Earth's ocean floor. The detection of hydrogen in Enceladus's plumes strongly suggests that similar reactions are occurring at the bottom of the Moon's ocean, where hot water is circulating through the rocky core. This hydrothermal activity would provide both heat and chemical energy, creating conditions that could potentially support life. The discovery of phosphorus in the plumes, announced in 2023, added another essential piece to the habitability puzzle. Phosphorus is a key element for life as we know it, a component of DNA, RNA, and the energy-carrying molecule ATP. Its presence in Enceladus's ocean means that all 6 of the elements most important for life are available there: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The concentration of phosphorus detected was surprisingly high, suggesting that the chemical conditions in Enceladus's ocean may be particularly favourable for the chemistry of life. The plumes also carry information about the physical conditions in the ocean and the fractures through which the material escapes. The velocity of the ejected particles tells us about the pressure driving the eruptions. The temperature of the plume material, measured by infrared instruments, reveals how warm the fractures are. The variation in plume activity with Enceladus's orbital position shows how tidal forces affect the opening and closing of the vents. All of this information helps scientists build models of the plume system, understanding how material travels from the ocean to space. One of the most remarkable aspects of the plumes is their accessibility. On most ocean worlds, the subsurface water is hidden beneath kilometers of ice, inaccessible to any spacecraft we could currently build. On Enceladus, the ocean delivers samples of itself directly to space, where they can be collected and analysed by passing spacecraft. This accessibility makes Enceladus uniquely valuable for astrobiology, offering a way to search for signs of life without the enormous technical challenges of drilling through an ice shell. A spacecraft flying through the plumes can sample ocean water that has been conveniently delivered to its instruments, analysing it for biosignatures and other indicators of habitability. The question of whether the plumes sample the deep ocean directly or draw from shallower reservoirs within the ice shell remains an active area of research. Some models suggest that the plume material comes straight from the ocean, travelling up through the tiger stripe fractures without significant modification. Other models propose that the water passes through intermediate chambers or pockets within the ice, where it might be altered by freezing and thawing processes. Understanding the plume source is important for interpreting the chemical data and for planning future life detection missions. Regardless of their exact source, the plumes have transformed our understanding of Enceladus and its potential for life. Before Cassini discovered them, Enceladus was an interesting but not particularly remarkable moon, one of dozens orbiting Saturn with no special claim to attention. The plumes revealed that this small world is actively connected to its interior. That material from below is continuously escaping into space. That the moon is geologically alive in a way that few had imagined possible. This discovery elevated Enceladus to the front rank of astrobiological targets, a world where the search for life might actually succeed. As you drift further into relaxation, imagine the plumes rising from Enceladus's south pole, graceful fountains of ice and vapour catching the distant sunlight, glittering against the blackness of space. Each particle in those plumes is a tiny ambassador from the ocean below, carrying information about a world we have never seen, a world that might harbour life. The plumes are Enceladus's voice, speaking to us across the vastness of space, inviting us to come closer, to listen more carefully, to discover what secrets the deep might hold. Chapter 16. Companions in the Dark. Enceladus and Saturn's other moons. Enceladus does not orbit Saturn alone. It is one member of a vast family of moons, more than 140 known satellites that range from tiny irregular fragments to world-sized bodies with their own complex geology and atmospheres. Understanding Enceladus requires understanding its place within this family, the gravitational relationships that connect it to its siblings, and the ways in which it differs from and resembles the other moons of Saturn. The innermost of Saturn's major moons is Mimas, a body similar in size to Enceladus but strikingly different in character. Mimas is dominated by a single enormous impact crater, Herschel, which gives the moon an appearance reminiscent of the Death Star from Star Wars. Unlike Enceladus, Mimas shows no signs of geological activity. Its surface is ancient and heavily cratered, unchanged for billions of years. The contrast between these two similarly sized moons is one of the great puzzles of planetary science. Why is Enceladus so active while Mimas is so dead? The answer may lie in their different internal structures, their different orbital histories, or factors we have not yet identified. Moving outward from Enceladus, we encounter Tethys, another icy moon with a heavily cratered surface and a great rift valley called Ithaca Chasma that stretches across much of its circumference. Tethys is larger than Enceladus, about 160 kilometers in diameter, but like Mimas, it shows no signs of current geological activity. Its surface records the history of impacts over billions of years, a frozen chronicle of the bombardment that has affected all bodies in the outer solar system. Dione, the moon whose gravitational resonance with Enceladus helps maintain the smaller moon's orbital eccentricity and thus its tidal heating, is a world of contrasts. Some regions of Dione are heavily cratered and ancient, while others show evidence of past geological activity, including bright ice cliffs called chasmata that may have formed through tectonic processes. Dione is thought to have a subsurface ocean of its own, though much deeper and less accessible than Enceladus's ocean. The gravitational dance between Dione and Enceladus has shaped both moons over billions of years, linking their fates in ways that are still being unravelled. Rhea, the second largest of Saturn's moons after Titan, is another heavily cratered world with little evidence of recent geological activity. Its surface is ancient and battered, recording the history of impacts since the early days of the solar system. Rhea may have a thin ring system of its own, though this remains controversial, and it may have a tenuous atmosphere of oxygen and carbon dioxide. But compared to the dynamic activity of Enceladus, Rhea is a quiet world, its geological fires long since extinguished. And then there is Titan, Saturn's largest moon, and one of the most remarkable worlds in the solar system. Titan is larger than the planet Mercury, with a thick atmosphere of nitrogen and methane that obscures its surface from view. Beneath that atmosphere lies a landscape of hydrocarbon lakes and seas, rivers and rain, dunes and mountains, a world with weather and seasons, and a complexity that rivals Earth's. Titan also has a subsurface ocean of liquid water, detected through measurements of how the moon's shape changes as it orbits Saturn. But this ocean lies far beneath the surface, inaccessible to the plume sampling that makes Enceladus so attractive for astrobiology. The diversity of Saturn's moons reflects the complex history of the Saturnian system, the varied conditions under which these worlds formed and evolved. Some moons, like Enceladus, have remained geologically active throughout their history, their interiors kept warm by tidal heating or other processes. Others, like Mimas and Rhea, froze solid early in their history and have remained unchanged ever since. Still others, like Titan, have developed in unique ways, their size and composition leading to outcomes unlike anything else in the solar system. Enceladus's relationship with Saturn's E-ring connects it to the broader Saturnian environment in a tangible way. The E-ring is the widest of Saturn's rings, extending from inside the orbit of Mimas to beyond the orbit of Titan, a span of nearly 1 million kilometres. This ring is composed of tiny ice particles, most of them less than a micrometer in diameter, that are continuously being lost to various processes and must be continuously replenished. Enceladus, through its plume activity, is the source of this replenishment, single-handedly maintaining a planetary ring through its geological activity. The particles ejected by Enceladus's plumes follow various trajectories depending on their size and initial velocity. The smallest particles are pushed outward by the pressure of sunlight and by interactions with Saturn's magnetic field, spreading the E-ring over its enormous extent. Larger particles fall back to Enceladus's surface, coating the Moon in a continuous snow of fresh ice that contributes to its exceptional brightness. Some particles are swept up by other moons, coating their surfaces with material from Enceladus's ocean. The E-ring is thus a visible manifestation of Enceladus's activity, a ring of ice that traces the Moon's influence throughout the Saturnian system. The interaction between Enceladus and Saturn's magnetosphere adds another dimension to the Moon's influence on its environment. Saturn has a powerful magnetic field that traps charged particles in radiation belts similar to Earth's Van Allen belts. When Enceladus's plumes eject water vapor and ice particles into space, some of this material becomes ionized by solar radiation, creating charged particles that interact with Saturn's magnetic field. These interactions create disturbances in the magnetosphere that were detected by Cassini's instruments, providing some of the earliest hints that Enceladus was actively venting material into space. The water molecules ejected by the plumes are broken apart by solar ultraviolet radiation, a process called photodissociation that splits water into hydrogen and oxygen atoms. These atoms can then be ionized by further radiation or by collisions with other particles, becoming charged ions that are picked up by Saturn's rotating magnetic field. The result is a torus of plasma, a donut-shaped region of charged particles centered on Enceladus's orbit, that affects the behavior of Saturn's magnetosphere in measurable ways. This plasma torus is another manifestation of Enceladus's activity, an invisible ring of charged particles that complements the visible E-ring of ice. The influence of Enceladus extends even to Saturn's atmosphere. Some of the water molecules ejected by the plumes eventually find their way to Saturn itself, falling into the planet's upper atmosphere and affecting its chemistry. This influx of water from Enceladus was detected by observations from Earth-based telescopes and later confirmed by Cassini, demonstrating that the small moon is actively modifying the atmosphere of its giant parent planet. The amount of water delivered is small compared to Saturn's total atmospheric mass, but it is enough to affect the chemistry of the upper atmosphere, creating observable signatures that link the planet to its active moon. The moons of Saturn interact with each other in complex ways beyond the orbital resonances that maintain their orbits. Material ejected from Enceladus coats the surfaces of nearby moons, affecting their appearance and surface properties. The inner moons, which orbit within or near the E-ring, are particularly affected by this coating, their surfaces brightened by the continuous fall of ice particles from Enceladus. Even distant moons may receive some contribution from Enceladus's plumes, though the effect diminishes with distance as the E-ring particles spread out and are lost to various processes. The study of Saturn's moons as a system, rather than as isolated individuals, has been one of the great advances of the Cassini era. Before Cassini, we knew the moons primarily as points of light, or at best, as fuzzy images with limited detail. Cassini revealed them as worlds in their own right, each with its own character and history, but also as members of a family, connected by gravity and by the exchange of material. Enceladus, with its plumes and its E-ring, is the most dramatic example of this interconnection. But all of Saturn's moons are linked in ways that we are still working to understand. The comparison between Saturn's moons and Jupiter's moons is instructive. Jupiter has 4 large moons, the Galilean satellites, each of which is world-sized and geologically complex. Io is the most volcanically active body in the solar system, its surface continuously renewed by eruptions of sulfur and silicate lava. Europa has a subsurface ocean that may be habitable, hidden beneath an ice shell crisscrossed by fractures and ridges. Ganymede is the largest moon in the solar system, with its own magnetic field and a deep ocean sandwiched between layers of ice. Callisto is heavily cratered and ancient, but may also harbour a subsurface ocean. These 4 moons dominate Jupiter's satellite system, dwarfing the dozens of smaller irregular moons that orbit at greater distances. Saturn's moon system is different, with one giant moon, Titan, and a collection of medium-sized icy moons that includes Enceladus. This different architecture reflects the different histories of the 2 planetary systems, the different conditions under which their moons formed and evolved. The presence of Titan, with its thick atmosphere and complex surface, gives Saturn's system a unique character, while the activity of Enceladus provides a counterpoint to Europa in the search for habitable environments. Together, the moon systems of Jupiter and Saturn offer a natural laboratory for studying the diversity of icy worlds and the conditions that lead to geological activity and potential habitability. As you continue to relax and let your thoughts drift, consider the family of moons that accompanies Enceladus in its orbit around Saturn. Each of these worlds has its own story, its own history, its own secrets waiting to be discovered. Some are ancient and unchanging, their surfaces recording billions of years of cosmic history. Others are dynamic and active, their interiors still warm, their surfaces still being renewed. Together, they form a miniature solar system within the solar system, a diverse collection of worlds united by their common parent planet. Chapter 17. The Colours of Ice, Understanding Enceladus's Surface. The surface of Enceladus is a study in contrasts, a world where ancient cratered terrain gives way to young smooth plains, where fractures and ridges record the history of tectonic forces, where the continuous fall of plume material creates the brightest surface in the solar system. Understanding this surface requires careful analysis of images and measurements from Cassini, combined with models of the processes that have shaped the moon over billions of years. The most striking characteristic of Enceladus's surface is its exceptional brightness. The moon reflects nearly all of the sunlight that falls on it, with an albedo, or reflectivity, of approximately 99. This makes Enceladus the most reflective body in the solar system, brighter even than fresh snow on Earth. The reason for this extreme brightness is the continuous coating of fresh ice particles from the plumes, which fall back to the surface and cover any older, darker material that might accumulate from impacts or space weathering. Enceladus is essentially cleaning itself continuously, maintaining its pristine appearance through its own geological activity. The colour of Enceladus's surface is predominantly white, as expected for a world covered in water ice. However, careful analysis of Cassini images reveals subtle colour variations across the surface, hints of slightly different compositions or textures in different regions. Some areas show a slight bluish tint, which may indicate smaller ice grain sizes or the presence of certain impurities. Other areas appear slightly more yellow or tan, possibly due to organic compounds or other non-ice materials mixed with the ice. These colour variations are subtle and difficult to detect, but they provide clues to the processes that have shaped different parts of the surface. The cratered terrain on Enceladus records the history of impacts over billions of years. These craters range in size from tiny pits to large basins tens of kilometers across. Their forms modified by the flow of ice and the relaxation of topography over time. The largest craters have flat floors and subdued rims, their original sharp features softened by the slow creep of ice under Enceladus's weak gravity. Smaller craters retain more of their original form, their bowl shapes still visible despite billions of years of exposure to the space environment. The distribution of craters across Enceladus's surface is not uniform. Some regions are heavily cratered, their surfaces recording impacts since the early days of the solar system. Other regions have far fewer craters, indicating that they have been resurfaced more recently, their older craters erased by geological processes. The South Polar region, where the tiger stripes are located, has almost no craters at all, suggesting that this area has been continuously resurfaced by plume activity and is geologically very young. This variation in crater density allows scientists to estimate the ages of different surface regions, building up a timeline of Enceladus's geological history. The smooth plains on Enceladus are among the youngest surfaces in the solar system. These regions are characterized by a near-complete absence of craters and a relatively flat topography, suggesting that they have been flooded by some material that covered the older terrain. The most likely explanation is cryovolcanism, the eruption of water or water ice mixtures onto the surface, where they freeze and form new terrain. This process is analogous to volcanism on Earth, but with water playing the role of lava. The smooth plains may represent ancient episodes of cryovolcanic activity, periods when liquid water or slush reached the surface and spread across the landscape before freezing solid. The fractures and ridges that crisscross Enceladus's surface record the tectonic forces that have acted on the Moon over its history. These features form when the ice shell is stretched, compressed, or sheared by forces from within, cracking and deforming in response to stresses that exceed the strength of the ice. The patterns of fractures and ridges vary across the surface, reflecting different stress regimes in different regions and at different times. Some fractures run parallel to each other in orderly arrays, while others intersect at various angles, creating complex networks that challenge interpretation. The tiger stripes are the most dramatic tectonic features on Enceladus, the fractures from which the plumes erupt. These features are unique in the solar system, active vents that connect the surface to the ocean below and allow material to escape into space. The tiger stripes are warm compared to the surrounding terrain, their temperatures elevated by the heat escaping from the interior. They are also young, probably only a few million years old based on the scarcity of superimposed craters. The opening of the tiger stripes may have marked the beginning of the current phase of plume activity, a geological event that transformed Enceladus from a more quiescent world into the active moon we observe today. The terrain between the tiger stripes, known as the South Polar terrain, is some of the most complex and interesting on Enceladus. This region is characterized by a chaotic jumble of ice blocks, ridges and fractures, a landscape that speaks to intense geological activity. The ice here has been broken and refrozen multiple times, creating a surface that is difficult to interpret, but clearly records a dynamic history. Some scientists have suggested that this terrain formed through a process similar to sea ice formation on Earth, with slabs of ice breaking apart, drifting, and refreezing in new configurations. The boundary between the South Polar terrain and the older cratered terrain to the north is marked by a distinctive belt of ridges and grooves that encircles the South Pole. This boundary represents a fundamental division in Enceladus's geology, separating the young, active south from the old, quiescent north. The origin of this asymmetry is not fully understood, but it may be related to the way tidal heating is distributed within the Moon, with heat concentrated at the South Pole for reasons that are still being investigated. As you rest and your breathing continues to slow, imagine the surface of Enceladus stretching out beneath you, a landscape of ice in shades of white and subtle blue, cratered plains giving way to smooth terrains, fractures and ridges casting long shadows in the distant sunlight. This surface has been shaped by billions of years of geological processes, by impacts and tectonics and cryovolcanism, by the continuous fall of ice from the plumes above. It is a surface that records history, that tells stories to those who know how to read it, that invites exploration and discovery. Chapter 18. The Mathematics of Wonder. Enceladus by the Numbers. Sometimes the best way to appreciate a world is through the numbers that describe it, the measurements and calculations that quantify its properties and place it in context. Enceladus is a world of remarkable numbers, figures that capture its size, its orbit, its activity, and its potential for life. Let us explore some of these numbers, allowing them to paint a picture of this small moon in precise mathematical terms. Enceladus has a mean diameter of 504.2 kilometers, making it roughly 1/7 the diameter of Earth's moon, and small enough to fit within the borders of the state of Arizona or the nation of Spain. Despite its small size, Enceladus has a mass of approximately 108 billion kilograms, enough to generate a surface gravity of 0.113 meters per second squared, about 1% of Earth's gravity. On Enceladus, you would weigh about 100 times less than you do on Earth, and you could jump to heights that would be impossible on our planet. The Moon orbits Saturn at a mean distance of 237,948 kilometers, completing one orbit every 32.9 hours. This orbital period means that Enceladus experiences about 266 orbits per Earth year, each one bringing a cycle of tidal flexing that contributes to the Moon's internal heating. The orbit is nearly circular, with an eccentricity of just 0.0047, but this small deviation from perfect circularity is enough to drive significant tidal heating when combined with the gravitational influence of Dione. The surface temperature of Enceladus varies depending on location and time of day, but averages around 75 Kelvin or minus 198 degrees Celsius. This is cold enough that water ice behaves like rock, hard and brittle rather than soft and flowing. However, the tiger stripes are significantly warmer, with temperatures reaching as high as 197 Kelvin or minus 76 degrees Celsius in some locations. This temperature difference of over 100 degrees between the tiger stripes and the surrounding terrain is a direct result of heat escaping from the interior through these active fractures. The plumes of Enceladus eject material at velocities of approximately 400 meters per second, fast enough to escape the Moon's weak gravity and enter orbit around Saturn. The total mass ejection rate has been estimated at around 200 kilograms per second, though this figure varies depending on Enceladus's orbital position and the method of measurement. Over the course of a year, the plumes eject roughly 6 billion kilograms of material into space, enough to maintain Saturn's E-ring against the continuous losses that would otherwise cause it to dissipate. The subsurface ocean of Enceladus is estimated to lie beneath an ice shell that varies in thickness from perhaps 5 kilometers at the South Pole to 30 or 35 kilometers in other regions. The ocean itself may be around 10 kilometers deep on average, though it could be deeper beneath the South Pole where the ice shell is thinner. The total volume of the ocean is estimated at around 40 million cubic kilometres, comparable to the volume of Lake Superior multiplied by about 3,000 times, or roughly equivalent to all of Earth's liquid fresh water combined. The salinity of Enceladus's ocean, based on analysis of the plume particles, appears to be similar to, or slightly lower than, Earth's oceans, with a concentration of dissolved salts around 10 to 40 grams per kilogram of water. The pH of the ocean is estimated at 8 to 9, making it mildly alkaline, similar to baking soda dissolved in water. These conditions are well within the range that Earth organisms can tolerate, suggesting that the ocean would not be chemically hostile to life as we know it. The organic molecules detected in the plumes include compounds with masses up to and exceeding 200 atomic mass units, indicating the presence of complex carbon-based chemistry. The concentration of molecular hydrogen in the plumes has been measured at around 0.4 to 1.4% by volume, consistent with production by serpentinization reactions at hydrothermal vents. The concentration of phosphorus, announced in 2023, was found to be at least 100 times higher than in Earth's oceans, suggesting that this essential element for life is abundant in Enceladus's ocean. The power output from Enceladus's south polar region, representing heat escaping from the interior, has been estimated at around 4 to 18 gigawatts, depending on the measurement technique and assumptions used. For comparison, this is roughly equivalent to the output of several large nuclear power plants, a substantial amount of energy for such a small world. This heat is generated by tidal flexing and is what maintains the liquid ocean and powers the plume activity. The age of the tiger stripes and the south polar terrain is estimated at less than 10 million years, and possibly much younger based on the scarcity of impact craters. This makes the south polar region one of the youngest surfaces in the solar system, continuously renewed by plume activity and tectonic processes. In contrast, the heavily cratered terrain in other parts of Enceladus may be billions of years old, recording impacts since the early days of the solar system. The distance from Earth to Enceladus varies depending on the positions of the planets in their orbits, but averages around 1.4 billion kilometers. At this distance, light takes about 79 minutes to travel from Enceladus to Earth, meaning that any signal from a spacecraft at Enceladus would take over an hour to reach us. This communication delay makes real-time control of spacecraft impossible and requires that any mission to Enceladus be highly autonomous, capable of making decisions and responding to situations without waiting for instructions from Earth. These numbers, dry as they may seem, capture something essential about Enceladus. They describe a world that is small but not insignificant, cold but not dead, distant but not unreachable. They quantify the conditions that make Enceladus potentially habitable, the properties that set it apart from other moons, the characteristics that make it such a compelling target for exploration. Numbers are the language of science, and in that language, Enceladus speaks of wonder. Chapter 19. Voices of Discovery. The scientists who revealed Enceladus. Behind every discovery about Enceladus are the scientists who made it, the men and women who dedicated years of their lives to studying this distant moon and unravelling its secrets. Their work spans decades and continents, involving thousands of researchers from dozens of countries, all contributing to our understanding of this remarkable world. Let us take a moment to appreciate some of the voices of discovery, the scientists whose insights have shaped our knowledge of Enceladus. The Cassini mission, which revealed so much about Enceladus, was the product of a vast international collaboration. The spacecraft was built by NASA's Jet Propulsion Laboratory in California, with contributions from the European Space Agency and the Italian Space Agency. The scientific instruments were designed and built by teams from universities and research institutions around the world, each bringing unique expertise to the mission. And the scientists who analysed the data came from an even broader community, united by their curiosity about Saturn and its moons. Caroline Porco, the leader of Cassini's imaging team, played a central role in the discovery and study of Enceladus's plumes. Her team was responsible for the cameras that captured the first images of the jets erupting from the tiger stripes, images that changed our understanding of what small icy moons can do. Porco has been a tireless advocate for Enceladus exploration, arguing that the moon's accessible ocean makes it the best place in the solar system to search for extraterrestrial life. Her passion for Enceladus has inspired countless others to take this small moon seriously as an astrobiology target. Hunter Waite, the principal investigator for Cassini's ion and neutral mass spectrometer, led the efforts to analyse the composition of the plumes. His team was responsible for detecting the molecular hydrogen that suggests hydrothermal activity, the complex organic molecules that indicate rich chemistry, and many of the other compounds that make Enceladus's ocean so intriguing. Waite's careful analysis of the mass spectrometer data has been essential for understanding what the plumes tell us about the ocean below. Christopher Glein, a geochemist who has worked extensively on Enceladus, has been instrumental in interpreting the chemical data from the plumes. His models of the ocean's chemistry have helped constrain its pH, salinity, and potential for supporting life. Glein was part of the team that announced the discovery of phosphorus in the plumes, a finding that significantly strengthened the case for Enceladus's habitability. His work bridges the gap between spacecraft measurements and our understanding of ocean world chemistry. Frank Postberg, a planetary scientist at the Free University of Berlin, has been a leader in analysing the composition of the ice particles in Enceladus's plumes. His work on the Cosmic Dust Analyzer instrument has revealed the presence of salts, organic molecules, and other compounds that provide clues to the ocean's nature. Postberg led the study that announced the discovery of complex organic molecules in the plumes, a finding that made headlines around the world and added to the excitement about Enceladus's potential for life. Jonathan Lunine, a planetary scientist at Cornell University, has been a prominent voice in advocating for future Enceladus exploration. He has contributed to numerous mission concepts and studies, helping to define the scientific goals and technical requirements for returning to this small moon. Lunine's vision of Enceladus as a place where we might actually find life has helped shape the priorities of the planetary science community and has influenced the direction of future exploration planning. These scientists, and hundreds of others whose names may be less familiar, have devoted their careers to understanding Enceladus. They have spent long hours analysing data, writing papers, attending conferences, and debating interpretations. They have experienced the thrill of discovery and the frustration of uncertainty. They have built a body of knowledge about Enceladus that did not exist before, transforming a point of light into a world we can begin to understand. Their work is a testament to the power of human curiosity and the value of sustained scientific investigation. The international nature of Enceladus research reflects the global character of modern planetary science. Scientists from the United States, Europe, Japan, and many other countries have contributed to our understanding of this moon, sharing data and ideas across borders and boundaries. The Cassini mission itself was a collaboration between NASA and the European Space Agency, with contributions from the Italian Space Agency and scientific teams from around the world. This international cooperation has been essential for the success of outer solar system exploration, pooling resources and expertise that no single nation, could provide alone. The next generation of Enceladus scientists is already being trained, students and young researchers who will carry the torch of exploration into the future. They are learning the techniques of planetary science, studying the data from Cassini, and dreaming of the missions that might one day return to this small moon. Some of them will lead those future missions, making discoveries that we cannot yet imagine. The story of Enceladus is not just a story of the past, it is a story that continues to unfold, written by each new generation of curious minds. As you rest and let your thoughts drift, consider the human element of Enceladus exploration, the scientists who have devoted their lives to understanding this distant world. They are people like you, driven by curiosity and wonder, seeking to understand our place in the universe. Their discoveries have expanded our horizons and challenged our assumptions, revealing that even small distant moons can be worlds of extraordinary interest. Their work continues, and the story they are telling is far from finished. Chapter 20. Dreams of ice and water, imagining life on Enceladus. What might life on Enceladus look like? This question has fascinated scientists and dreamers since the discovery of the plumes, inspiring speculation about the forms that alien organisms might take in the dark, cold waters beneath the ice. While we have no evidence that life actually exists on Enceladus, the exercise of imagining what it might be like helps us think about the possibilities and prepares us for what we might find when we finally go looking. If life exists on Enceladus, it almost certainly consists of microorganisms, simple single-celled creatures similar to the bacteria and archaea that dominate Earth's biosphere. The conditions in Enceladus's ocean, while potentially habitable, are unlikely to support the complex multicellular life that we are most familiar with on Earth. The energy available from hydrothermal vents and chemical reactions is probably limited, supporting only small populations of simple organisms rather than the abundant ecosystems we find in Earth's sunlit oceans. Life on Enceladus, if it exists, would be sparse and simple, but no less remarkable for that. The most likely habitat for life on Enceladus would be the seafloor, where hydrothermal vents release heat and chemicals from the moon's interior. On Earth, hydrothermal vents support thriving communities of microorganisms that derive energy from chemical reactions rather than sunlight, a process called chemosynthesis. These microbes form the base of food chains that support larger organisms, including tube worms, clams and shrimp, that have adapted to the extreme conditions of the deep sea. On Enceladus, similar microbes might cluster around hydrothermal vents, feeding on the hydrogen and other chemicals released by serpentinization reactions in the rocky core. The microbes of Enceladus, if they exist, might use metabolic pathways similar to those of Earth's chemosynthetic organisms. One possibility is methanogenesis, the production of methane from hydrogen and carbon dioxide, a metabolism used by many archaea on Earth. The detection of both hydrogen and methane in Enceladus's plumes has led some scientists to speculate that methanogenic organisms might be present, producing the methane as a byproduct of their metabolism. However, methane can also be produced by non-biological processes, so its presence alone does not prove the existence of life. Another possible metabolism for Enceladus life is sulfate reduction, the use of sulfate ions as an electron acceptor in place of oxygen. This metabolism is common among bacteria in Earth's deep subsurface and ocean sediments, environments that share some characteristics with Enceladus's ocean. Sulfate has been detected in the plumes, suggesting that it is available in the ocean, and the reducing conditions indicated by the presence of hydrogen would favour this type of metabolism. Sulfate-reducing organisms on Enceladus might form biofilms on rocks near hydrothermal vents, slowly extracting energy from the chemical gradients in their environment. The physical form of Enceladus microbes is harder to predict, but they would likely be small, perhaps a micrometer or less in diameter, similar to the smallest bacteria on Earth. They might have cell walls to protect them from the high pressures of the deep ocean, and they might produce antifreeze compounds to prevent ice crystals from forming inside their cells. Their biochemistry might be based on the same fundamental molecules as Earth life, DNA and RNA and proteins, or it might use alternative systems that we have not yet imagined. The discovery of life on Enceladus would tell us whether our biochemistry is universal or just one of many possible solutions to the challenges of living. Some scientists have speculated about more exotic forms of life on Enceladus, organisms that might inhabit niches other than the seafloor vents. Life might exist within the ice shell itself, in pockets of liquid water or in thin films of water between ice crystals. It might drift in the water column, carried by currents through the ocean, feeding on organic particles that rain down from above or well up from below. It might even exist in the plumes themselves, microbes lofted from the ocean and ejected into space, surviving briefly in the vacuum before falling back to the surface or escaping into Saturn's E-ring. The possibility of life in the plumes has important implications for future exploration. If microbes are present in the ejected material, they might be detectable by spacecraft flying through the plumes, their cells or cellular components captured and analysed by onboard instruments. This would be an extraordinary discovery, proof of life beyond Earth obtained without ever landing on the surface or penetrating the ice shell. The accessibility of the plumes is one of Enceladus's great advantages as an astrobiology target, offering a chance to sample the ocean directly and search for signs of life in material conveniently delivered to space. The search for life on Enceladus would need to distinguish between living organisms and the chemical signatures they might leave behind. Biosignatures, the markers of biological activity, can include specific molecules like amino acids and lipids, isotopic ratios that differ from non-biological processes, and structural features like cell membranes and organelles. A comprehensive life detection strategy would look for multiple independent biosignatures, building a case for life through converging evidence rather than relying on any single measurement. This approach reduces the risk of false positives, ensuring that any claim of life detection is robust and defensible. The ethical implications of finding life on Enceladus have also been considered by scientists and philosophers. If life exists there, it would have value in its own right, regardless of its utility to humans. We would need to consider how to study it without harming it, how to protect it from contamination by Earth organisms, and how to balance our desire for knowledge against our responsibility to preserve what we find. These questions are not merely academic. They would become urgent practical matters if life were actually discovered, requiring careful thought and international cooperation to address. As you drift deeper into relaxation, let your imagination wander through the dark waters of Enceladus's ocean. Picture the seafloor, dimly lit by the glow of hydrothermal vents, where hot water laden with chemicals emerges from cracks in the rock. Imagine tiny organisms clustered around these vents, drawing energy from the chemical reactions, living their microscopic lives in a world utterly unlike our own. Whether or not such life actually exists, the possibility is enough to inspire wonder, to remind us that the universe may be far more alive than we know. Chapter 21. The Long View, Enceladus in Deep Time. The story of Enceladus stretches back billions of years to the formation of the solar system itself. Understanding this deep history helps us appreciate how this small moon came to be what it is today. the processes that shaped it over eons, and the future that may await it in the billions of years to come. Let us take the long view, considering Enceladus in the context of deep time. The solar system formed approximately 4.6 billion years ago from a cloud of gas and dust that collapsed under its own gravity. At the centre of this cloud, the Sun ignited, while the remaining material coalesced into planets, moons, asteroids, and comets. Saturn formed in the outer solar system, where temperatures were cold enough for volatile compounds like water and ammonia to condense into solid ice. Around Saturn, a disk of gas and dust gave rise to the planet's rings and moons, including the small icy body that would become Enceladus. The early history of Enceladus is obscured by time, but we can make educated guesses based on our understanding of moon formation and the evidence preserved on the moon's surface. Enceladus likely formed from the accretion of ice and rock in the disk around Saturn, growing gradually as particles collided and stuck together. The heat of formation, combined with the decay of radioactive elements in the rocky component, would have warmed the young moon's interior, potentially melting some of the ice and creating an early ocean. During the first billion years of solar system history, a period known as the Late Heavy Bombardment, Enceladus would have been subjected to intense cratering as leftover debris from planet formation rained down on all the solid bodies in the solar system. The heavily cratered terrain on parts of Enceladus's surface dates from this era, recording the scars of ancient impacts that have been preserved for billions of years. These old surfaces tell us that Enceladus has existed since the early days of the solar system, a witness to the violent processes that shaped our cosmic neighbourhood. The evolution of Enceladus's interior over billions of years is a complex story that scientists are still working to understand. At some point, the Moon developed the orbital resonance with Dione that maintains its orbital eccentricity and drives tidal heating today. This resonance may have formed gradually as the orbits of Saturn's moons evolved, or it may have been established early in the system's history. Once the resonance was in place, tidal heating would have begun, warming the interior and potentially maintaining or creating a liquid water ocean. The history of Enceladus's geological activity is recorded in the different terrains on its surface. The ancient cratered terrain represents periods when the surface was relatively quiescent, accumulating impact craters without being erased by geological processes. The younger, smoother terrains represent episodes of resurfacing, times when cryovolcanism or other processes covered the older surface with fresh material. The tiger stripes and south polar terrain represent the most recent phase of activity, perhaps beginning only a few million years ago and continuing to the present day. The question of whether Enceladus's activity has been continuous or episodic over its history is an active area of research. Some models suggest that tidal heating has been relatively steady, maintaining a liquid ocean throughout most of the Moon's history. Other models propose that the activity has waxed and waned, with periods of intense heating alternating with quieter phases. The distribution of surface terrains, with their varying ages and degrees of resurfacing, supports the idea of episodic activity, but the details remain uncertain. Looking to the future, Enceladus will continue to orbit Saturn, its plumes spraying material into space, its ocean churning beneath the ice. The orbital resonance with Dione should remain stable for billions of years, ensuring that tidal heating continues and the ocean remains liquid. The tiger stripes may eventually close, and new fractures may open elsewhere, shifting the location of plume activity over time. The E-ring will continue to be replenished by the plumes, a visible testament to Enceladus's ongoing activity. On longer timescales, the future of Enceladus depends on the future of the solar system itself. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to expand into a red giant, growing so large that it will engulf the inner planets. Saturn will remain safely distant, but the increased solar luminosity will warm the outer solar system, potentially affecting Enceladus and other icy moons. The ice shell might thin or even disappear, exposing the ocean to space. The ultimate fate of Enceladus in this distant future is uncertain, but it will likely remain a recognizable world for billions of years to come. The deep time perspective reminds us that Enceladus is not a static snapshot, but a dynamic world with a history and a future. The moon we observe today is just one moment in a story that spans billions of years, a story that began with the formation of the solar system and will continue long after we are gone. Understanding this history enriches our appreciation of Enceladus, placing our observations in context and reminding us that the processes we see today have been operating for eons. As your mind continues to relax and your thoughts grow quieter, consider the vast stretches of time that have shaped Enceladus into the world it is today. Billions of years of impacts and tectonics, of heating and cooling, of ice and water and rock interacting in the darkness of the outer solar system. This history is written on the moon's surface and in its interior, waiting to be read by those patient enough to study it. And the story continues, unfolding in real time as the plumes spray and the ocean churns, adding new chapters to a tale that began when the solar system was young. Chapter 22, a gentle closing, drifting among the stars. And so we come to the end of our journey through the story of Enceladus, though in truth the story has no end. The plumes continue to spray, the ocean continues to churn, the moon continues its eternal dance around Saturn. Scientists continue to analyze data and plan future missions, seeking answers to the questions that Enceladus has raised, questions about the nature of this small moon and the possibility of life in its hidden waters. The story we have told tonight is just one chapter in a much longer narrative, a narrative that began billions of years ago and will continue for billions of years more. As you lie here, feeling the gentle weight of sleep beginning to settle over you, let your mind hold the image of Enceladus one last time. Picture that small bright moon orbiting Saturn, its surface gleaming white in the distant sunlight, its south pole wreathed in the delicate spray of its plumes. Beneath that frozen surface, an ocean of liquid water stretches in perpetual darkness, warmed by the heat of tidal flexing, stirred by currents we can only imagine. At the bottom of that ocean, hydrothermal vents may be releasing heat and chemicals into the water, creating conditions that might, just might, support life. This image of Enceladus is one of the great gifts of the space age, a vision of another world that our ancestors could never have imagined. William Herschel, peering through his telescope on that August night in 1789, saw only a tiny point of light moving against the background of stars. He could not have known that this point of light was a world with an ocean, with geysers, with the potential for life. He could not have imagined the spacecraft that would one day visit this moon, the instruments that would analyze its plumes, the scientists who would debate its habitability. Yet his discovery was the first step on a journey that has brought us to where we are today, standing on the threshold of perhaps the greatest discovery in human history. The search for life beyond Earth is one of the most profound endeavours our species has ever undertaken. It speaks to our deepest questions about who we are and our place in the universe. Are we alone? Is Earth the only world where life has taken hold, a singular miracle in an otherwise barren cosmos? Or is life common, arising wherever conditions permit, filling the universe with organisms of every conceivable form? These questions have been asked for centuries, but only now do we have the tools to begin answering them. And Enceladus with its accessible ocean and its spraying plumes, offers perhaps our best chance of finding that answer within our lifetimes. If we find life on Enceladus, it will change everything. It will tell us that life is not unique to Earth, that the processes that gave rise to life here can occur elsewhere, that the universe is more alive than we ever dared to hope. It will raise new questions about the nature of life, its origins, its diversity, its distribution across the cosmos. It will challenge us to think about our responsibilities to other living things, even microscopic ones on distant moons. And it will inspire us to continue exploring, to seek out other worlds where life might exist, to push the boundaries of our knowledge ever further into the unknown. If we search and find nothing, that too will be meaningful. It will tell us that life is rare, that the conditions for its origin are more stringent than we thought, that Earth may be more special than we realized. It will remind us of the preciousness of our own world, the only place we know for certain harbours life, and of our responsibility to protect it. And it will not end the search, for absence of evidence is not evidence of absence, and there are many other worlds to explore, many other oceans to sample, many other questions to ask. Either way, the exploration of Enceladus is a worthy endeavour, a testament to human curiosity and ingenuity, a reaching out across the vastness of space to touch another world. The scientists who study Enceladus, the engineers who build the spacecraft, the dreamers who imagine what we might find, all are participating in one of humanity's great adventures. And you, listening to this story, learning about this distant moon, wondering about the possibilities it represents, you too are part of this adventure. Your curiosity connects you to the long chain of explorers who have sought to understand the universe, from the ancient astronomers who first mapped the stars to the modern scientists who send robots to other worlds. The night sky, if you could see it now, would be filled with stars, each one a sun like our own, many of them orbited by planets and moons we have not yet discovered. Among those countless worlds, there may be other Enceladuses, other small moons with hidden oceans and spraying plumes, other places where life might exist in the darkness beneath the ice. The universe is vast beyond comprehension, and we have only begun to explore it. The story of Enceladus is just one small part of a much larger story, the story of life in the cosmos, a story that is still being written. As sleep draws closer and your thoughts grow softer, let yourself drift among the stars. Imagine floating in the darkness of space, surrounded by the gentle glow of distant suns, watching as Saturn turns slowly on its axis, its rings catching the light, its moons tracing their orbits in the eternal dance of gravity. Among those moons, small and bright, Enceladus continues its journey, spraying its plumes into the void, sending samples of its ocean out into space, inviting us to come and discover what secrets it holds. The plumes of Enceladus are a kind of beacon, a signal from a world that wants to be explored. They announce to the cosmos that this small moon is special, that something remarkable is happening beneath its frozen surface, that here is a place worth visiting, worth studying, worth understanding. We have heard that signal, and we have responded with curiosity and wonder. We have sent our spacecraft to investigate, our instruments to analyze, our minds to interpret. And we have learned that Enceladus is indeed special, a world with an ocean, with chemistry, with energy, with all the ingredients that life requires. The future of Enceladus exploration is bright with possibility. New missions are being planned, new technologies are being developed, new questions are being formulated. Someday, perhaps within your lifetime, a spacecraft will return to Enceladus, flying through its plumes with instruments designed specifically to search for signs of life. It will sample the ice particles and water vapour, analysing them for amino acids and lipids, for cellular structures and metabolic byproducts, for any hint that life exists in that distant ocean. And when the results come back, transmitted across more than 1 billion kilometers of space, we will know at last whether we are alone. Until that day, Enceladus remains a world of mystery and promise, a place where our imagination can roam freely, where we can dream of what might be. The ocean beneath the ice is a realm we have never seen, a place of perpetual darkness and cold, yet potentially teeming with life. The hydrothermal vents on the seafloor, if they exist, might be oases of warmth and energy, gathering places for organisms that have never known sunlight, that have evolved in isolation for billions of years. What forms might such life take? What metabolisms might it use? What would it mean for our understanding of biology, of evolution, of the nature of life itself? These questions have no answers yet, but the asking of them is itself valuable. It stretches our minds, challenges our assumptions, prepares us for discoveries that might overturn everything we think we know. The history of science is filled with such overturnings, moments when new evidence forced us to abandon old ideas and embrace new ones. The discovery of life on Enceladus, if it comes, would be one of the greatest such moments, a revolution in our understanding of the universe and our place in it. But for now, let these thoughts fade gently into the background as sleep approaches. Let the image of Enceladus become a peaceful presence in your mind, a reminder of the wonders that exist beyond our small world, the mysteries that await our exploration, the possibilities that the universe holds. The story of Enceladus is a story of hope, of curiosity, of the human spirit reaching out across the cosmos to touch the unknown. It is a story that belongs to all of us, a shared heritage of discovery that connects us to each other and to the universe we inhabit. The night is quiet now, and the stars are shining in the darkness above. Somewhere out there, beyond the Moon and Mars, beyond the asteroid belt and Jupiter, Saturn orbits the Sun with its family of moons. And among those moons, small and bright and full of secrets, Enceladus continues its eternal journey, its plumes spraying, its ocean churning, its story unfolding in the silence of space. Sleep now, and let that image carry you into dreams, dreams of ice and water, of hidden oceans and distant worlds, of the endless adventure of exploration that defines us as a species. The universe is vast and ancient, filled with wonders we have not yet discovered, mysteries we have not yet solved, questions we have not yet asked. Enceladus is just one small part of this vast cosmos, but it is a part that speaks to us, that invites us to learn more, that promises revelations if we are patient and persistent enough to seek them. The scientists who study Enceladus are our emissaries to this distant world, carrying our curiosity across the solar system, returning with knowledge that enriches us all. As your breathing slows and your body relaxes more deeply, feel the peace that comes from contemplating the cosmos. The worries and concerns of daily life seem small against the backdrop of the universe, the billions of years of history, the countless worlds that exist beyond our own. Enceladus has been orbiting Saturn for longer than life has existed on Earth, and it will continue orbiting long after we are gone. There is comfort in this perspective, a reminder that we are part of something much larger than ourselves, a cosmic story that began long before us and will continue long after. The plumes of Enceladus spray continuously, day and night, year after year, century after century. They have been spraying for millions of years, perhaps longer, and they will continue for millions of years more. Each particle of ice that rises from the tiger stripes is a tiny piece of the ocean below, a sample of a world we have never seen, a message from the deep. These messages have been sent for eons, but only now have we developed the ability to receive them, to read them, to understand what they tell us about this remarkable moon. In the grand sweep of cosmic time, Our exploration of Enceladus is just beginning. The Voyager flybys were the first tentative steps, brief glimpses of a world we did not yet understand. The Cassini mission was a deeper engagement, years of study that revealed the plumes and the ocean and the potential for life. Future missions will go further still, sampling the plumes directly, landing on the surface, perhaps even penetrating the ice to explore the ocean below. Each step brings us closer to understanding Enceladus, closer to answering the questions that drive our exploration. But tonight, let all of that fade into the background. Let the facts and figures, the scientific details and mission plans drift away like clouds dispersing in a gentle breeze. What remains is the wonder, the sense of awe that comes from contemplating a world so different from our own, yet potentially harbouring the same spark of life that animates our planet. Enceladus is a mirror in which we see ourselves reflected, our curiosity, our hope, our longing to know that we are not alone in the universe. Sleep now, and let the story of Enceladus accompany you into the night. Let it be a gentle presence in your dreams, a reminder of the beauty and mystery that exist beyond our small world. The universe is full of wonders, and Enceladus is one of the most wonderful of all. A small moon with a big story, a frozen world with a liquid heart, a place where the conditions for life may exist in the darkness beneath the ice. The stars are shining, the night is deep, and somewhere far away, Enceladus orbits Saturn in the silence of space. Its plumes spray upward, catching the distant sunlight, glittering like fountains of diamonds against the blackness of the void. Its ocean churns in the darkness below, warmed by the heat of tidal flexing, stirred by currents that flow from pole to pole. And in that ocean, in the warmth near hydrothermal vents, in the chemical-rich waters where rock meets water, life may be waiting to be discovered. Rest now, and let these images carry you gently into sleep. The story of Enceladus will be here when you wake, waiting to be continued, waiting for the next chapter to be written. For now, let peace settle over you like a blanket of fresh snow, soft and quiet and comforting. The universe is vast and full of wonders, and you are part of it, connected to the stars and planets and moons by the atoms in your body, by the curiosity in your mind, by the dreams that carry you through the night. Good night, and may your dreams be filled with the gentle wonder of distant worlds.